Hey guys, tonight we begin with a story that reaches back through time to one of the most dramatic turning points in the history of life itself, when the first animals decided they needed protection. And let me tell you, this wasn't a gradual suggestion from nature. This was a biological arms race so intense it fundamentally changed what it meant to be alive on planet Earth. So before you settle in, take a moment to like the video and subscribe, but only if you genuinely enjoy diving deep into the mysteries of ancient life. And let me know in the comments where you're watching from and what fascinates you most about prehistoric creatures. Now dim the lights, maybe grab a warm drink, and let's journey back to a time when the very concept of armor was being invented for the first time. Picture this. 550 million years ago, Earth's oceans were about to witness something unprecedented. The first animals were experimenting with something that had never existed before: protective shells. Not the elaborate fortresses we see in modern crabs or the spiraling masterpieces of snails, but crude, simple tubes made of calcium carbonate. These early pioneers had no blueprint to follow, no evolutionary manual to consult. They were writing the rules of biological warfare as they went along. The star of this ancient drama was a creature called Claudina. Now, Claudina wasn't much to look at. Picture a tiny cone-shaped tube, barely a few millimeters long, nestled inside slightly larger tubes like a set of Russian dolls made of stone. These little calcium carbonate cones were clustered together in colonies across the seafloor, marking the very first time in Earth's history that animals had figured out how to build themselves protective armor from scratch. But here's where it gets fascinating. Scientists have found Claudina fossils riddled with perfectly round holes, not random damage from decay or geological pressure. These are predatory boreholes. Someone, or rather something, was hunting these early shell builders with enough precision to drill clean through their protective armor. We're talking about holes that are proportional to the size of the Claudina specimens, showing that predators were selecting their targets carefully. Even more remarkably, many specimens show multiple boreholes, meaning these ancient animals survived repeated attacks. Their armor was working, at least partially. This discovery represents the earliest direct evidence of predation in the fossil record. Think about that for a moment. The very first shells ever built were already being tested in combat. Before complex eyes, before sophisticated hunting strategies, before most of the biological innovations we associate with predation, something was already out there attacking armored prey with surgical precision. The evolutionary arms race between predator and prey didn't develop gradually over millions of years. It exploded into existence almost the moment animals figured out how to build protective shells. But Claudina was just the opening act. What came next would make those simple nested tubes look like Stone Age tools compared to modern technology. We're talking about the Cambrian explosion, a period roughly 540 million years ago when life on Earth went from relatively simple and soft to complex and armored in what amounts to a geological instant. This wasn't just evolution, this was biological revolution. The Cambrian period marked the moment when practically all major animal groups started appearing in the fossil record with hard shells, spines, and protective plates. We're talking about trilobites with their sophisticated compound eyes and segmented armor, brachiopods with their hinged shells, early mollusks experimenting with spiral protection, arthropods developing everything from simple carapaces to elaborate spinal defenses. In just a few million years, the seafloor transformed from a place of soft, vulnerable creatures to an underwater battlefield, where armor became the price of admission to survival. Now, you might be wondering what triggered this sudden explosion of biological innovation. The answer isn't simple, because multiple factors converged at exactly the right moment to create the perfect storm for armor evolution. But one of the most crucial developments was the rise of vision. Imagine living in a world where predators hunted primarily by chemical cues, touch, or random encounters. Your best defense strategy would be to hide, move carefully, or simply avoid detection. But the moment predators developed complex eyes, the entire game changed. Trilobites, those iconic Cambrian arthropods, possess some of the most sophisticated eyes in the animal kingdom. We're talking about compound eyes with hundreds or even thousands of individual lenses, each made from calcite crystal that was so pure it was essentially distortion-free. These weren't primitive light sensors. These were precision optical instruments that could spot prey from considerable distances across the ancient seafloor. Once vision became widespread, there was no hiding in plain sight. Animals needed physical protection that could withstand direct assault. The evolutionary pressure shifted from avoiding detection to surviving attack. And this pressure was intense enough to drive some of the most rapid morphological changes in the history of life. But vision was just one piece of the puzzle. The chemistry of ancient oceans played an equally crucial role in determining when animals could build their protective shells. During the late Ediacaran and early Cambrian periods, ocean chemistry underwent dramatic changes that made biomineralization not just possible, but relatively easy. The ratio of magnesium to calcium in seawater shifted in ways that favored the precipitation of calcite, the primary building material for early shells. This chemical shift reduced the energetic cost of building calcium carbonate armor, making it accessible to a much broader range of organisms. Suddenly, creatures that had never been able to afford the metabolic expense of shell building found themselves with access to biological construction materials. It was like discovering that steel had become cheap and abundant right when you needed to build better fortifications. Oxygen levels also played a critical role in this armored revolution. Higher atmospheric and oceanic oxygen concentrations provided the metabolic fuel necessary to power larger, more active animals. But more importantly, increased oxygen levels gave organisms the energetic capacity to build and maintain calcium carbonate shells, which are metabolically expensive to produce. Without sufficient oxygen, the complex biochemical processes involved in biomineralization simply wouldn't have been feasible for most early animals. The fossil record shows us that the earliest experiments with armor weren't always successful. Scientists have discovered thousands of tiny shell fragments from the early Cambrian called small shelly fossils. These represent the building blocks of the armor revolution, consisting of everything from simple protective plates to complex spinal elements. Many of these early attempts at protection were crude by modern standards, but they demonstrate that biomineralization was not a sudden invention. It was a gradual process of experimentation with different materials, structures, and protective strategies. Some of these early armored pioneers developed truly bizarre defensive strategies. Take Shishania aculeata, a 514 million-year-old fossil that reveals how early mollusks approached the problem of protection. Rather than building a single protective shell, Shishania was covered in hundreds of tiny spinal cones, each secreted through an internal system of microscopic canals. These spines were so small that their internal structure is barely visible even under powerful microscopes. Yet they represent sophisticated biological engineering that rivals anything produced by modern shell-building animals. The discovery of Shishania tells us something profound about early armor evolution. The ancestors of all modern mollusks, creatures that would eventually give us everything from snails to giant clams, started out as armored spiny slugs. They experimented with protective spines long before they developed the single shells we associate with modern gastropods and bivalves. This suggests that armor evolution was a process of trial and error, with different lineages exploring various defensive strategies before settling on the designs that proved most effective. But perhaps the most remarkable aspect of early armor evolution was how quickly organisms could adapt their defensive strategies in response to predatory pressure. Recent research on a tiny Cambrian brachiopod called Lapoethella fasciculata provides direct evidence of rapid evolutionary responses to attack. Scientists studying hundreds of these microscopic shells found that they became progressively thicker over a relatively short period of geological time, coinciding with an increase in predatory boreholes. This represents the earliest demonstrable record of an evolutionary arms race in action. Predators were drilling through shells, so prey species responded by building thicker armor. The predators then adapted to penetrate the improved defenses, driving further innovations in protective shell design. This cycle of attack and counterattack played out over thousands of generations, compressed into what amounts to a brief moment in geological time. What makes this arms race even more fascinating is that it wasn't just about large predators attacking visible prey. Recent discoveries have revealed that early shells were also sophisticated biochemical barriers against microbial attack. The calcareous shells of the earliest mollusks developed advanced internal tubule systems that evolved primarily as a defensive strategy against extensive microbial attacks. These high-density tubules comprised approximately 35% of shell volume, enabling early armored animals to cope with increasing microbial bioerosion caused by boring bacteria and cyanobacteria. This means that early armor served a dual purpose. It protected against large predators that could be seen and avoided, but it also defended against microscopic enemies that were invisible but equally deadly. The evolution of biomineralization was therefore a multifaceted response to the full spectrum of biological threats that early animals faced in their increasingly dangerous world. As we delve deeper into this armored revolution, one thing becomes crystal clear. The development of shells and protective structures wasn't just about individual survival. It fundamentally changed the nature of marine ecosystems, creating new ecological niches and driving the evolution of increasingly complex communities. The simple act of building a shell opened up entirely new ways of living, feeding, and interacting with other organisms. The story of early armor is ultimately a story about innovation under pressure. When faced with new threats, life found ways to adapt that were both elegant and effective. From the nested tubes of Cloudina to the compound eyes of trilobites, from the spinal defenses of early mollusks to the rapid evolutionary responses of tiny brachiopods, each innovation built upon previous discoveries to create increasingly sophisticated systems of protection and survival. The trilobites deserve special attention here, because they represent perhaps the most successful early experiment in biological armor design. These arthropods didn't just stumble into protective shells. They engineered sophisticated defense systems that would make a modern military contractor jealous. Their segmented exoskeletons were marvels of biological engineering, constructed from calcified plates that could flex and articulate while maintaining structural integrity under attack. But the real genius of trilobite armor wasn't just in its construction, it was in its versatility. When danger approached, many trilobite species could roll themselves into perfect spheres, protecting their soft undersides while presenting attackers with nothing but armored curves. This enrollment behavior, as paleontologists call it, was so effective that we find countless fossilized trilobite balls scattered throughout Cambrian rock formations. These aren't death poses. These are defensive positions, frozen in time like ancient soldiers taking cover. The sophistication of trilobite enrollment goes far beyond simple ball formation. Different species developed distinct rolling strategies based on their specific anatomy and the threats they faced. Some could achieve complete enrollment, sealing themselves into impenetrable spheres. Others developed partial enrollment techniques that protected vital organs while maintaining some mobility. The mechanics required precise coordination between dozens of body segments, each equipped with specialized joints and muscle systems that had to work in perfect synchronization. What's even more remarkable is how quickly trilobites evolved increasingly elaborate defensive features. Early Cambrian species had relatively simple, smooth exoskeletons. But as predatory pressure intensified throughout the Paleozoic era, trilobites responded with biological arms escalation. that reads like a catalogue of medieval weaponry. Spines erupted from their shells in every conceivable configuration. Some species developed forward-pointing defensive spikes. Others bristled with lateral projections that made them nearly impossible to swallow. The most extreme forms looked more like underwater porcupines than arthropods. Consider Drotops armatus, a Devonian trilobite that took spinal defense to its logical extreme. This creature was so thoroughly armored with protective spikes that it resembled a biological fortress more than a living animal. Every segment of its exoskeleton sprouted defensive projections, creating a nearly impenetrable barrier against the giant predators that stalk the Devonian seas. These weren't random evolutionary accidents. Each spike was positioned with mechanical precision to provide maximum protection while minimizing interference with essential functions like feeding and locomotion. The evolution of trilobite eyes represents another crucial breakthrough in the armor revolution. These weren't simple light sensors like we see in many primitive organisms. Trilobite eyes were compound structures made from hundreds or thousands of individual calcite lenses, each precisely shaped to focus light without distortion. The mineral calcite was the perfect choice for biological optics because of its unique crystalline structure, which naturally eliminates the spherical aberration that plagues most biological lenses. But trilobite vision wasn't just about seeing clearly, it was about seeing first. In the predator-prey arms race that defined early marine ecosystems, the ability to spot threats or opportunities from a distance provided enormous survival advantages. Trilobites with superior vision could detect approaching predators earlier, giving them crucial extra seconds to deploy their defensive strategies. They could also identify optimal feeding areas and potential mates from greater distances, expanding their ecological options in ways that purely defensive adaptations couldn't match. The relationship between vision and armor created a fascinating feedback loop in early marine evolution. Better eyesight led to more effective hunting, which increased predatory pressure on armored prey. This drove the evolution of more sophisticated defensive strategies, which in turn selected for predators with even keener vision and more advanced attack methods. The result was an escalating cycle of biological innovation that pushed both predators and prey toward increasingly complex and specialized forms. Meanwhile, other groups were experimenting with entirely different approaches to the armor problem. Early brachiopods developed hinged shells that could snap shut at the first sign of danger, creating living fortresses that could seal themselves off from the outside world. These weren't crude clam-like devices. Brachiopod shells were precision instruments with complex hinge mechanisms that allowed for controlled opening and closing while maintaining perfect seal integrity when closed. The internal structure of brachiopod shells reveals sophisticated biological engineering that rivals modern composite materials. Alternating layers of organic and mineral components created shells that were both lightweight and incredibly strong. The organic layers provided flexibility and crack resistance, while the mineral layers contributed rigidity and crushing strength. This laminated construction distributed stress loads across multiple layers, preventing catastrophic failure even under severe attack. Early mollusks took yet another approach to biological protection. Rather than building heavy, rigid shells like brachiopods, they experimented with curved and spiral designs that could deflect attacks while maintaining streamlined profiles for efficient movement. The mathematics behind these early spiral shells demonstrate that even primitive mollusks had somehow discovered optimal engineering solutions for combining protection with hydrodynamic efficiency. The fossil record reveals that mollusk shell evolution proceeded through distinct phases of experimentation. Early forms like Shishania represented the spinal defense approach, covering themselves with hundreds of tiny protective cones. Later species began experimenting with single-shell designs, gradually refining the shape and structure until they achieved the elegant spiral forms we associate with modern gastropods. Each evolutionary step built upon previous innovations while exploring new possibilities for combining protection with functionality. But the armor revolution wasn't limited to large, visible creatures. Some of the most important innovations occurred at microscopic scales, where early animals had to defend themselves against threats that were invisible to the naked eye. Bacterial and cyanobacterial borers could slowly dissolve calcium carbonate shells from within, creating a constant threat that required sophisticated biochemical defenses. The response to microbial attack led to some of the most ingenious biological engineering solutions in the early fossil record. Shell-building organisms developed internal canal systems that could actively transport defensive chemicals to sites of bacterial attack. These tubular networks function like biological plumbing systems, delivering antimicrobial compounds exactly where they were needed while maintaining the structural integrity of the shell itself. The metabolic cost of maintaining these complex defense systems was enormous. Early armored animals had to dedicate significant portions of their energy budgets to shell construction and maintenance. This created strong selective pressure for efficient biomineralization processes and optimal shell designs that provided maximum protection for minimum metabolic investment. The organisms that survived were those that found the sweet spot between defensive effectiveness and energetic sustainability. Ocean chemistry continued to play a crucial role throughout this period of rapid armor evolution. Fluctuations in calcium and carbonate ion concentrations affected the ease of shell building, creating windows of opportunity for biomineralization, followed by periods when shell construction became energetically prohibitive. These chemical cycles helped drive the episodic nature of armor innovation, with major evolutionary breakthroughs often coinciding with favorable ocean chemistry conditions. The relationship between oxygen levels and armor evolution proved more complex than initially understood. While higher oxygen concentrations provided the metabolic fuel necessary for expensive shell construction, recent research suggests that many early armored animals actually thrived in low oxygen environments. Trilobites, in particular, developed respiratory systems that were specifically adapted to function efficiently in oxygen-poor waters. This adaptation to variable oxygen conditions may have actually favored certain types of armor development. Animals living in low oxygen environments needed efficient respiratory systems that could maximize oxygen uptake from limited supplies. The gill structures found in early trilobites show sophisticated adaptations for oxygen extraction, including elongated filaments and expanded surface areas that could function effectively even when oxygen levels dropped to levels that would be lethal to modern marine animals. The geographic distribution of early armored fossils tells us that armor evolution wasn't a localized phenomenon. From the tropical seas of ancient Laurentia to the deeper waters surrounding Gondwana, similar defensive innovations appeared independently across the globe. This suggests that the selective pressures driving armor evolution were fundamental features of early marine ecosystems, not regional anomalies or temporary environmental fluctuations. The speed of these evolutionary changes remains one of the most striking aspects of the early armor revolution. Geological timescales that represent mere moments in Earth's history witnessed transformations that fundamentally altered the nature of life itself. Species that had existed for millions of years as soft-bodied organisms suddenly developed sophisticated protective shells within a few 100,000 years. Predatory boring techniques evolved and counter-evolved so rapidly that we can trace the escalation through sequential rock layers. This rapid pace of innovation suggests that early marine ecosystems were under intense selective pressure from multiple sources simultaneously. Predation pressure from large hunters, microbial attacks from bacteria and cyanobacteria, competition for resources, and changing environmental conditions all contributed to an evolutionary crucible that forged some of the most important biological innovations in Earth's history. The legacy of this ancient armor revolution extends far beyond the Cambrian period itself. The basic biomineralization techniques developed by these early pioneers provided the foundation for virtually all subsequent shell-building innovations. Modern corals, mollusks, echinoderms, and countless other groups still rely on biochemical pathways, and structural principles that were first explored by Cambrian armor pioneers over 500 million years ago. 100 million years ago. The fossil record preserves an extraordinary catalogue of these early defensive innovations, each one representing a successful solution to the fundamental problem of staying alive in an increasingly dangerous world. But as we examine these ancient armored remains more closely, we begin to see patterns that reveal just how sophisticated these early defense systems actually were. These weren't random evolutionary accidents or crude approximations of modern shells. They were precisely engineered biological solutions that often surpassed anything we see in contemporary marine environments. Take the small shelly fossils that litter early Cambrian rock formations, like microscopic pieces of an ancient jigsaw puzzle. Each fragment tells a story of biological experimentation on a scale that dwarfs anything happening in modern oceans. Scientists have catalogued thousands of different shell types from this period, representing countless attempts to solve the armor problem using different materials, geometries, and construction techniques. Some built layered composite structures that distributed stress across multiple planes. Others experimented with hollow chambers that provided buoyancy while maintaining protective strength. Still others developed interlocking plate systems that could flex under pressure without breaking. The diversity of these early solutions demonstrates something profound about the nature of evolutionary innovation under pressure. When survival is at stake, life explores every possible avenue simultaneously. The Cambrian seas became a vast laboratory where different lineages tested competing approaches to biological defense, with natural selection serving as the ultimate quality control mechanism. Only the most effective designs survived to leave descendants. But the fossil record preserves evidence of countless failed experiments that pushed the boundaries of what was biologically possible. One of the most remarkable aspects of early shell chemistry involves the precision with which these ancient animals controlled mineral precipitation. Building a calcium carbonate shell isn't simply a matter of extracting materials from seawater and depositing them randomly. It requires sophisticated biochemical machinery that can regulate crystal growth, control shell thickness, and incorporate organic components in exactly the right proportions. The fact that animals developed these capabilities so quickly after the first appearance of predatory pressure suggests that the underlying biochemical pathways were already present, waiting to be activated by the right selective pressures. Recent analysis of shell microstructures from early Cambrian fossils reveals construction techniques that wouldn't look out of place in a modern materials science textbook. Alternating layers of organic and mineral components created composite materials with properties that exceeded either component alone. Organic layers provided flexibility and energy absorption, while mineral layers contributed rigidity and compressive strength. The interfaces between these layers were often structured at the molecular level to maximize bonding strength and prevent delamination under stress. But perhaps the most ingenious aspect of early shell design was how these animals solved the fundamental trade-off between protection and mobility. A shell that's thick enough to stop a determined predator might be too heavy for efficient locomotion. A shell that's light enough for rapid movement might offer inadequate protection against serious attacks. Early armored animals had to find the optimal balance point between these competing demands, and the solutions they developed often involved architectural innovations that maximize strength while minimizing weight. The mathematics behind these early shell designs reveals optimization principles that wouldn't be formally described by human engineers for another 500 million years. Spiral shells, for instance, follow logarithmic growth patterns that maintain constant proportions as the animal grows larger. This allows the shell to provide consistent protection throughout the organism's lifetime, while accommodating dramatic changes in body size. The fact that multiple lineages independently discovered these mathematical relationships suggests that there are fundamental physical laws governing optimal shell design. The internal architecture of early shells was equally sophisticated. Many species developed complex canal systems that served multiple functions simultaneously. These networks transported nutrients to growing shell margins, delivered defensive chemicals to sites under bacterial attack, and provided pathways for waste removal from shell-building tissues. The engineering required to coordinate these multiple functions within the constraints of a protective shell represents biological problem-solving at its finest. As predatory pressure intensified throughout the early Paleozoic, we see clear evidence of escalating defensive innovations in the fossil record. Shell thickness increased steadily over geological time, but not uniformly. Instead, animals developed strategies for concentrating protective material exactly where it was most needed, while keeping other areas relatively thin to minimize weight. This selective reinforcement required sensory systems that could detect and respond to localized attack patterns, suggesting that early armored animals possessed surprisingly sophisticated threat assessment capabilities. The development of repair mechanisms represents another crucial innovation from this period. Shells that could heal from damage provided enormous survival advantages over those that couldn't. The biochemical pathways required for shell repair involve complex coordination between immune systems, mineral transport networks, and growth regulation mechanisms. The fact that these systems evolved so early in armor development history indicates that shell maintenance was immediately recognized by natural selection as being just as important as initial construction. Evidence for rapid shell repair comes from fossils showing multiple generations of borehole healing. These specimens reveal that early armored animals could not only survive predatory attacks, but could restore their protective integrity quickly enough to withstand repeated assaults. The speed of this healing process, inferred from the microstructure of repair tissues, suggests metabolic investment in shell maintenance that rivaled the energy costs of initial construction. The geographic spread of armor innovations provides crucial insights into how defensive technologies propagated through early marine ecosystems. Fossil evidence indicates that successful shell designs could spread across entire ocean basins within a few million years, suggesting either rapid migration of armored species or independent evolution of similar solutions in response to similar selective pressures. The consistency of certain architectural features across widely separated fossil localities supports the idea that there are optimal engineering solutions to biological defense problems. Climate fluctuations during the early Cambrian period added another layer of complexity to armor evolution. Sea level changes, temperature variations, and shifts in ocean chemistry created constantly changing environmental conditions that affected both the availability of shell-building materials and the metabolic costs of biomineralization. Animals that could adjust their shell construction strategies in response to these environmental changes gained significant advantages over those with more rigid approaches. The relationship between shell chemistry and environmental conditions reveals sophisticated adaptation mechanisms that allowed early armored animals to thrive across diverse habitats. Species living in deeper, colder waters developed shells with different mineral compositions than those inhabiting shallow, warm seas. These chemical adjustments optimize shell properties for local conditions while maintaining essential protective functions. Trace fossil evidence from this period shows that armored animals quickly began to exploit new ecological niches that had been previously inaccessible to soft-bodied organisms. Burrow systems became more complex as armored animals developed the structural support necessary to excavate and maintain elaborate underground networks. Surface trails show evidence of more aggressive foraging behavior as protective shells allowed animals to venture into previously dangerous feeding areas. The coevolution of predatory and defensive strategies created feedback loops that accelerated innovation on both sides of the biological arms race. Predators that developed more effective attack methods gained access to previously protected prey resources, but this success immediately selected for improved defensive countermeasures. The result was a continuous cycle of innovation that pushed both predators and prey toward increasingly sophisticated capabilities. Isotopic analysis of early shell materials provides direct evidence for the metabolic costs of armor construction. The energy required to build and maintain calcium carbonate shells was substantial, often representing a significant fraction of an animal's total metabolic budget. This investment was clearly worthwhile, given the survival advantages provided by effective armor, but it also meant that shell-building animals had to develop more efficient feeding and energy storage strategies to support their defensive infrastructure. The transition from soft-bodied to armored ecosystems fundamentally altered nutrient cycling patterns in early marine environments. Calcium carbonate shells represented a new form of biological carbon storage that could persist long after the death of the organism. This created new biogeochemical pathways that affected ocean chemistry on a global scale, potentially influencing the availability of shell-building materials for future generations. Competition between different armor-building lineages drove the exploration of alternative shell materials and construction techniques. While calcium carbonate became the dominant choice for biological armor, early experiments included shells made from silica, phosphate minerals, and various organic composites. Each material offered different advantages and limitations, and the eventual dominance of calcium carbonate shells reflects the optimal balance of availability, strength, and metabolic cost under early marine conditions. The preservation bias in the fossil record means that we see only a fraction of the armor innovations that actually occurred during this period. Soft organic armor, which may have been just as important as mineralized shells, rarely preserves in ancient sediments. Recent discoveries of exceptionally preserved fossils hint at the existence of sophisticated organic protective systems that complemented or preceded mineralized armor in many lineages. Biomechanical analysis of fossilized shells reveals that early armored animals achieved remarkable efficiency in their defensive designs. Finite element modeling of trilobite exoskeletons shows stress distribution patterns that minimize material usage while maximizing protective coverage. These optimization strategies suggest that natural selection rapidly identified and refined the most effective architectural solutions for biological defense. The social implications of armor evolution extended far beyond individual protection. Armored animals could engage in more aggressive territorial behaviors, leading to the evolution of complex social hierarchies based on defensive capabilities. Shell ornamentation and specialized defensive structures may have served dual roles as both protective devices and social signals, allowing armored animals to assess potential competitors without engaging in dangerous direct confrontations. Chemical warfare emerged as another dimension of the predator-prey arms race during this period. Some early armored animals developed the ability to secrete toxic or deterrent compounds through their shells, adding biochemical defense to their physical protection. The integration of chemical and physical defensive strategies required sophisticated coordination between multiple organ systems and represents one of the earliest examples of combined defensive technologies in animal evolution. The success of early armor innovations created new selective pressures that continued to drive evolutionary change long after the initial appearance of shells. Predators adapted by developing specialized shell-breaking appendages, drilling capabilities, and strategies for attacking vulnerable points in armored prey. This ongoing coevolutionary process ensured that neither predators nor prey could rest on their evolutionary achievements, maintaining constant pressure for continued innovation and improvement. As we trace the development of biological armor through these early periods, we see the emergence of design principles that would continue to influence animal architecture for hundreds of millions of years. The fundamental engineering challenges faced by early shell builders, the solutions they developed, and the evolutionary processes that refined these innovations established patterns that echo through the entire subsequent history of life on Earth. The armor revolution wasn't just a historical event. It was the beginning of an ongoing conversation between life and the physical world, mediated by the eternal struggle between predator and prey. Struggle between predator and prey. The success of these early armored pioneers sent ripples through marine ecosystems that would reshape the entire biosphere. But the story takes a dramatic turn when we examine what happened to the animals that chose not to armor up. The fossil record from this period reveals a stark pattern of survival and extinction that reads like a biological version of natural selection in fast forward. Soft-bodied organisms that had dominated marine environments for millions of years suddenly found themselves at a devastating disadvantage. Without protective shells or defensive structures, they became easy targets for the new generation of visually guided predators that were spreading through Cambrian seas. The result was one of the most decisive evolutionary transitions in Earth's history, where the simple presence or absence of armor determined which lineages would survive to see the next geological period. But here's where the story becomes even more fascinating. Not every animal responded to predatory pressure by building thicker shells or sharper spines. Some species took the opposite approach, developing strategies to avoid confrontation entirely. These animals became the early masters of camouflage, burrowing, and rapid escape, creating an entirely parallel track of evolutionary innovation that focused on evasion rather than resistance. The fossil evidence for these alternative defensive strategies comes from trace fossils that preserve tracks and burrows that ancient animals left behind in seafloor sediments. During the early Cambrian, we see an explosion of burrow complexity that parallels the development of armor innovation. Simple vertical tubes gave way to elaborate branching networks, spiral constructions, and multi-level systems that provided both protection and access to food resources buried in marine sediments. These underground cities represent some of the most sophisticated architectural achievements in early animal evolution. The engineering required to excavate and maintain stable burrow systems in loose seafloor sediments demanded precise understanding of soil mechanics, structural support, and environmental conditions. Many of these burrow networks included specialized chambers for different functions, waste disposal areas, and emergency escape routes that could be activated when surface predators detected the burrow entrance. The animals that built these underground fortresses had to solve engineering problems that wouldn't be formally addressed by human engineers for hundreds of millions of years. How do you prevent tunnel collapse in unconsolidated sediments? How do you maintain adequate water circulation for respiration while keeping the burrow sealed against intruders? How do you balance the metabolic costs of excavation against the protective benefits of deeper, more complex burrows? The solutions preserved in Cambrian trace fossils reveal biological engineering principles that rival anything developed by modern burrowing animals. Spiral burrow designs distributed structural loads evenly while maximizing interior volume. Branching networks provided multiple escape routes while creating efficient systems for waste disposal and resource distribution. Chamber construction techniques concentrated protective space exactly where it was most needed while minimizing excavation costs. Meanwhile, on the ocean surface, another group of early animals was experimenting with mobility as their primary defense strategy. The development of sophisticated swimming capabilities required major innovations in body design, muscle systems, and sensory apparatus. Early swimmers had to solve the fundamental challenges of propulsion, steering, and buoyancy control while maintaining the speed necessary to outrun predators. The hydrodynamics of early swimming animals reveal optimization strategies that demonstrate remarkable understanding of fluid mechanics. Streamlined body shapes minimized drag, while specialized fin configurations provided precise control over movement direction and speed. The integration of sensory systems with propulsion mechanisms allowed early swimmers to detect threats and initiate escape responses faster than pursuing predators could adjust their attack strategies. But perhaps the most remarkable aspect of early swimming evolution was the development of jet propulsion systems in early cephalopods. These animals discovered that rapid water expulsion could generate thrust forces sufficient to achieve escape velocities that exceeded anything possible through conventional swimming. The biomechanics of jet propulsion required precise coordination between muscular contractions, valve systems, and directional control mechanisms that represented biological engineering at its most sophisticated. The fossil record preserves direct evidence of predator-prey chase sequences from this period, frozen in ancient seafloor sediments like stop-motion photographs of biological warfare. These trace fossils show the tracks of pursuing predators converging on the trails of potential prey, sometimes ending abruptly where successful attacks occurred, other times showing the divergent paths where prey animals successfully escaped. Analysis of these chase sequences reveals the tactical sophistication of early marine predators and the counter-strategies developed by their prey. Predatory tracks show evidence of coordinated hunting behaviors, ambush strategies, and persistence hunting techniques that required advanced cognitive capabilities. Prey trails demonstrate evasive maneuvers, false trail construction, and collaborative escape behaviors that suggest early development of social cooperation for mutual defense. The metabolic costs of these high-speed chase encounters placed enormous selective pressure on both predators and prey to develop more efficient energy systems. Animals engaged in predator-prey interactions needed rapid access to stored energy reserves, enhanced oxygen delivery systems, and waste removal capabilities that could function effectively during periods of maximum exertion. These physiological innovations laid the groundwork for the sophisticated cardiovascular and respiratory systems that characterize modern active animals. Chemical communication emerged as another crucial component of early marine ecosystems during this period. The ability to detect and respond to chemical signals allowed prey animals to identify approaching threats before visual contact occurred, providing crucial early warning systems that could mean the difference between life and death. Predators, in turn, developed strategies for masking their chemical signatures or exploiting the chemical signals produced by their prey. The biochemistry of early chemical communication required sophisticated molecular recognition systems that could distinguish between threat signals, food indicators, and social cues. The development of specialized chemoreceptor organs allowed early animals to sample and analyze complex chemical environments with precision that rivaled modern analytical instruments. These sensory innovations provided the foundation for complex behavioral responses that extended far beyond simple predator avoidance. Seasonal variations in predatory pressure created additional layers of complexity in early marine ecosystems. Breeding seasons, migration patterns, and resource availability cycles all influence the timing and intensity of predator-prey interactions. Animals that could predict and respond to these temporal patterns gained significant advantages over those with less flexible behavioral strategies. The fossil record from different seasons and environmental conditions reveals that early armored animals possessed remarkable behavioral flexibility. Shell ornamentation and defensive structures show seasonal variations that suggest animals could adjust their protective strategies based on anticipated threat levels. This adaptive capability required integration of environmental sensing, memory systems, and morphological plasticity that demonstrates sophisticated biological computation. Territory establishment and defense became increasingly important as armored animals developed the physical capabilities necessary to hold and protect valuable resources. The energy costs of shell construction meant that access to high-quality food sources and optimal shell building materials became crucial factors in survival and reproduction. Competition for these resources drove the evolution of complex territorial behaviors and social hierarchies. Archaeological evidence from this period includes fossilized shell accumulations that represent the earliest known animal construction projects. These shell middens, composed of discarded protective structures from multiple generations of shell-building animals, created elevated platforms that provided strategic advantages in territorial disputes. The construction and maintenance of these structures required coordinated group behaviors that represent early examples of animal cooperation. The relationship between body size and defensive strategy became increasingly important as predators developed more powerful attack capabilities. Larger animals could build thicker, more robust shells, but they also presented bigger targets and required more energy to maintain their defensive systems. Smaller animals could hide more effectively and required less energy for protection, but they had fewer options for withstanding direct attacks. This size-based arms race drove the evolution of specialized ecological niches based on different approaches to the protection problem. Giant armored animals dominated open water environments where their size and protective capabilities provided maximum advantage. Medium-sized animals specialized in complex habitats where maneuverability and behavioral flexibility were more important than raw defensive strength. Tiny armored animals exploited microhabitats where their small size allowed them to avoid detection entirely. The development of specialized attack strategies by predators created corresponding innovations in defensive countermeasures. Shell drilling techniques, which appeared early in the Cambrian period, drove the evolution of thicker shells with specialized internal structures designed to resist penetration. Crushing attacks led to the development of flexible shells that could deform without breaking. Toxin-based attacks selected for chemical detoxification systems and warning coloration patterns. Each new predatory innovation triggered cascading responses throughout marine food webs, as multiple prey species adapted to new threats simultaneously. The result was rapid coevolutionary change that affected entire ecosystems rather than just individual species pairs. This system-level evolution created the complex ecological networks that characterize modern marine environments. Reproductive strategies also evolved in response to increased predatory pressure during this period. Animals with effective armor could afford to invest more energy in reproduction, leading to increased population sizes and faster evolutionary change. Species with less effective defenses were forced to adopt reproductive strategies that emphasized rapid reproduction and high offspring numbers to compensate for increased mortality rates. The timing of reproductive activities became increasingly important as predatory pressure created seasonal windows of opportunity when breeding could occur safely. Many early armored animals developed synchronous reproduction strategies that overwhelmed predators with more potential prey than could be effectively attacked. These coordinated breeding events required sophisticated communication systems and environmental sensing capabilities. Parental care behaviors evolved rapidly during this period, as investment in individual offspring became more valuable when survival rates increased through effective protection. Early evidence for parental care includes fossilized brooding chambers within shells and protective structures that could shelter developing young. The metabolic costs of extended parental care required major changes in energy allocation strategies and reproductive timing. The integration of defensive and reproductive functions within single structures represents one of the most elegant solutions to the competing demands of survival and reproduction. Shells that could provide protection during normal activities while transforming into brood chambers during reproductive periods maximized the utility of expensive biological construction projects. These dual-purpose designs required sophisticated developmental control systems that could coordinate multiple functions within single anatomical structures. As predatory pressure continued to intensify throughout the Cambrian period, we begin to see evidence for the first collaborative defense strategies in the fossil record. Group formation behaviors allowed individual animals with limited defensive capabilities to achieve collective protection that exceeded what any single individual could provide. These early examples of cooperation under pressure laid the groundwork for the complex social behaviors that would evolve in later periods. The fossil evidence for early group defense includes mass mortality events, where numerous armored animals died together, while apparently attempting to protect shared resources or vulnerable group members. The spatial arrangements of these fossils suggest coordinated defensive formations that required communication, leadership, and individual sacrifice for group benefit. These behaviors represent sophisticated social cooperation that emerged directly from predatory pressure. Environmental engineering by early armored animals created positive feedback loops that enhanced the effectiveness of defensive strategies. Shell accumulations and burrow networks modified local seafloor conditions in ways that favored the animals that created them while making the environment less suitable for potential predators. These early examples of ecosystem engineering demonstrate how defensive innovations could create self-reinforcing advantages that persisted across multiple generations. The chemical modifications of seafloor environments by early shell builders affected local mineral availability, sediment stability, and water chemistry in ways that influenced the entire marine ecosystem. Areas with high concentrations of shell-building animals developed distinct chemical signatures that attracted additional shell builders while deterring predators that were adapted to different environmental conditions. Seasonal migration patterns emerged as another strategy for dealing with temporally variable predatory pressure. Animals that could track and exploit seasonal changes in predator distribution gained access to resources and breeding opportunities that were unavailable to less mobile species. These migration behaviors required sophisticated navigation capabilities and energy storage systems that could support long-distance movement. The fossil record preserves evidence of these early migration routes in the form of sequential fossil deposits that track the movement of armored animal populations across ancient seafloor landscapes. Analysis of these deposits reveals migration timing, route selection strategies, and stopover site characteristics that demonstrate remarkable behavioral sophistication in early marine animals. Communication systems evolved rapidly during this period, as the benefits of information sharing about predatory threats became increasingly important for survival. Early warning systems allowed armored animals to coordinate defensive responses across entire communities, multiplying the effectiveness of individual defensive capabilities. These communication networks required reliable signal transmission, message interpretation, and response coordination that pushed early nervous systems toward greater complexity. The biochemistry of early communication systems reveals sophisticated molecular mechanisms for signal production, transmission, and reception. Chemical signals could carry complex information about threat type, location, and intensity while remaining undetectable to potential predators. The development of species-specific communication channels allowed for secure information transfer within vulnerable populations. As we continue to trace the development of biological armor through this transformative period, we see the emergence of increasingly sophisticated integration between defensive structures, behavioral strategies, and ecological relationships. The simple shells and spines that mark the beginning of the armor revolution had evolved into complex biological systems that incorporated multiple defensive mechanisms within single anatomical frameworks. The engineering principles developed during this period of rapid innovation established design templates that would influence animal architecture for hundreds of millions of years. The fundamental trade-offs between protection and mobility, the optimization strategies for minimizing material costs while maximizing defensive effectiveness, and the integration of multiple functions within single structures all represent biological solutions to problems that continue to challenge modern engineers. But perhaps most remarkably, this entire transformation from soft-bodied to armored ecosystems occurred within a geological instant. The speed of innovation during the early Cambrian period demonstrates the enormous creative potential that emerges when life faces existential challenges. Under extreme selective pressure, biological systems can generate and test new solutions at rates that exceed anything seen in more stable environments. The legacy of this ancient arms race extends far beyond the specific innovations that emerged during the Cambrian period. The evolutionary processes that drove rapid defensive innovation established patterns of biological creativity and adaptation that continue to operate in modern ecosystems. Every time we see rapid evolutionary responses to new threats or opportunities, we're witnessing echoes of the same fundamental processes that created the first biological armor over 500 million years ago. The sophistication of these early defensive systems becomes even more apparent when we examine the microscopic details preserved in ancient shells. Modern scanning electron microscopy reveals that Cambrian armor wasn't crude or primitive by any measure. These early shell builders had mastered construction techniques that rival contemporary biological materials in their complexity and effectiveness. Consider the internal architecture of early brachiopod shells. These weren't simple calcium carbonate barriers slapped together in evolutionary haste. They were precision-engineered composite structures with alternating layers of organic and mineral components arranged in patterns that maximize strength while minimizing weight. The organic layers functioned like biological rebar, providing flexibility and preventing catastrophic crack propagation. The mineral layers contributed rigidity and compression resistance. The interfaces between these layers were structured at the molecular level to ensure optimal load transfer and prevent delamination under stress. But the real genius lay in how these animals controlled the construction process itself. Building an effective shell requires precise regulation of crystal growth, careful management of organic matrix deposition, and exact timing of mineralization events. The biochemical machinery necessary to coordinate these processes represents some of the most sophisticated cellular engineering in the early fossil record. Recent analysis of shell growth patterns reveals that early Cambrian animals possessed remarkable control over their construction projects. Daily growth increments preserved in ancient shells show that these animals could adjust shell thickness, modify internal structure, and alter chemical composition in response to changing environmental conditions or threat levels. This real-time construction management required sensory systems capable of detecting external conditions and cellular mechanisms that could translate environmental information into specific architectural modifications. The energy economics of early shell construction tell an equally fascinating story. Isotopic analysis of Cambrian shells reveals the metabolic costs associated with different construction strategies. Animals that built thicker, more protective shells invested enormous amounts of energy in their defensive systems, sometimes dedicating more than half their total metabolic budget to shell construction and maintenance. This level of investment was clearly worthwhile, given the survival advantages provided by effective armor, but it also meant that armored animals had to develop more efficient feeding strategies and energy storage systems to support their defensive infrastructure. The relationship between shell chemistry and local environmental conditions reveals another layer of sophistication in early armor systems. Animals living in different marine environments developed shells with distinct chemical signatures that were optimized for local conditions. Species in deeper, colder waters incorporated different trace elements than those inhabiting shallow, warm seas. These chemical adjustments fine-tuned shell properties for specific environmental challenges, while maintaining essential protective functions. The geographical distribution of shell chemistries across ancient ocean basins provides direct evidence for the environmental factors that influenced early armor evolution. Shells from tropical regions show chemical signatures consistent with rapid growth in warm, nutrient-rich waters. Specimens from polar regions reveal slower growth rates, but enhanced structural density that provided superior protection against the larger predators that dominated colder seas. Seasonal variations in shell chemistry demonstrate that early armored animals could adjust their construction strategies throughout the year in response to changing conditions. Shells laid down during winter months often show increased density and altered trace element compositions compared to summer growth increments. This seasonal tuning required sophisticated biological control systems that could integrate environmental sensing with metabolic regulation and construction planning. The repair mechanisms developed by early shell builders represent another remarkable innovation from this period. Shells that could heal from damage provided enormous survival advantages over those that couldn't. The biochemical pathways required for shell repair involve complex coordination between immune systems, mineral transport networks, and growth regulation mechanisms. Evidence from repaired bore holes in Cambrian fossils shows that these healing systems could restore structural integrity within days or weeks of attack, fast enough to provide protection against repeated assaults. The microstructure of repair tissues reveals construction techniques that differed significantly from normal shell growth patterns. Repair zones often show rapid deposition of protective material followed by gradual remodeling to restore optimal structural properties. This emergency construction capability required cellular mechanisms that could shift between normal growth mode and rapid response mode depending on damage assessment signals. Trace element analysis of repair zones provides insights into the metabolic costs of shell healing. Animals divert significant resources to damage repair, often depleting trace element reserves that would normally support other physiological functions. The speed and effectiveness of repair responses directly correlated with survival rates, creating strong selective pressure for efficient healing systems. The integration of repair capabilities with normal growth processes required sophisticated developmental control mechanisms. Animals had to balance investment in preventive shell thickening against reactive repair capabilities while maintaining optimal shell geometry for their specific ecological niche. The solutions preserved in Cambrian fossils reveal biological engineering principles that optimize protection across multiple timescales and threat scenarios. Competition between different shell-building lineages during this period drove exploration of alternative construction materials and techniques. While calcium carbonate became the dominant choice for biological armor, early experiments included shells made from silica, phosphate minerals, and various organic composites. Each material offered different advantages and limitations in terms of availability, strength, and metabolic cost. Silica-based shells provided superior hardness and resistance to chemical dissolution, but required different biochemical pathways for construction and imposed higher energy costs for repair. Phosphate shells offered excellent strength-to-weight ratios, but were more difficult to obtain in marine environments, where phosphorus availability was often limited. Organic composite shells provided maximum flexibility and repair capability, but offered less protection against crushing attacks. The eventual dominance of calcium carbonate shells reflects the optimal balance of material properties, environmental availability, and metabolic efficiency under early marine conditions. However, the experimental phase preserved in early Cambrian deposits reveals the remarkable range of solutions that life explored when faced with the fundamental challenge of biological protection. The relationship between shell construction and reproductive strategies created additional evolutionary pressures during this period. Animals with effective armor could afford to invest more energy in reproduction, leading to larger offspring sizes and enhanced parental care behaviors. The protective capabilities of shells also enabled new reproductive strategies that would have been impossible for soft-bodied animals. Brooding behaviors evolved rapidly among early shell builders as parents gained the ability to protect developing offspring within their own armor systems. Modified shell chambers provided safe spaces for embryonic development while maintaining the adult's mobility and feeding capabilities. The engineering required to create dual-purpose structures that functioned both as personal armor and nursery chambers represents remarkable biological problem-solving. The timing of reproductive activities became increasingly sophisticated as shell builders developed the ability to predict and respond to seasonal patterns in predatory pressure. Many species evolved synchronized breeding events that overwhelmed local predator populations with more potential prey than could be effectively attacked. These coordinated reproductive strategies required communication systems that could coordinate timing across entire populations. Chemical signaling systems evolved to support these reproductive coordination behaviors. Pheromone production and detection capabilities allowed shell builders to communicate reproductive readiness and coordinate spawning events across wide geographical areas. The biochemistry of these signaling systems required molecular recognition mechanisms that could distinguish between species-specific signals and general environmental cues. The development of specialized reproductive armor represents one of the most elegant solutions to the competing demands of protection and reproduction. Some early shell builders evolved modified shell structures that provided enhanced protection during vulnerable reproductive periods, while maintaining normal defensive capabilities during the rest of the year. These seasonal armor modifications required sophisticated developmental control systems that could coordinate structural changes with reproductive cycles. Parental care behaviors evolved rapidly during this period as investment in individual offspring became more valuable when survival rates increased through effective protection. Early evidence for parental care includes fossilized shells with specialized brood chambers and protective structures designed to shelter developing young. The metabolic costs of extended parental care required major changes in energy allocation strategies and reproductive timing. The integration of defensive and reproductive functions within single-shell structures maximized the utility of expensive biological construction projects. Shells that could provide protection during normal activities while transforming into brood chambers during reproductive periods represented optimal solutions to resource allocation challenges. These dual-purpose designs required developmental control systems that could coordinate multiple functions within single anatomical frameworks. Social behaviors also evolved in response to the new defensive capabilities provided by early armor systems. Group formation allowed individual animals with limited defensive capabilities to achieve collective protection that exceeded what any single individual could provide. The fossil record preserves evidence of coordinated group behaviors that emerged directly from predatory pressure. Mass mortality events from this period show spatial arrangements of armored animals that suggest defensive formations and cooperative behaviors. Groups of shell builders apparently coordinated their positioning to provide mutual protection while maintaining access to feeding opportunities. These behaviors required communication systems, leadership hierarchies, and individual decision-making capabilities that demonstrate sophisticated social cooperation. The chemical ecology of early shell-building communities reveals another dimension of social evolution during this period. Animals that could coordinate chemical defenses achieved collective protection that was more effective than individual chemical warfare strategies. Synchronized toxin production and chemical signal coordination created community-wide defensive networks that deterred predators across entire local ecosystems. Territory establishment and defense became increasingly important as shell builders developed the physical capabilities necessary to hold and protect valuable resources. The energy costs of shell construction meant that access to high-quality food sources and optimal shell-building materials became crucial factors in survival and reproduction. Competition for these resources drove the evolution of complex territorial behaviors. Archaeological evidence from this period includes fossilized shell accumulations that represent early animal construction projects. These shell middens, composed of discarded protective structures from multiple generations of shell builders, created elevated platforms that provided strategic advantages in territorial disputes. The construction and maintenance of these structures required coordinated group behaviors and long-term planning capabilities. Environmental engineering by early armored animals created positive feedback loops that enhanced the effectiveness of defensive strategies. Shell accumulations and burrow networks modified local seafloor conditions in ways that favored the animals that created them, while making the environment less suitable for potential predators. These ecosystem engineering effects demonstrate how defensive innovations could create self-reinforcing advantages. The chemical modifications of seafloor environments by early shell builders affected local mineral availability, sediment stability, and water chemistry in ways that influenced entire marine ecosystems. Areas with high concentrations of shell-building animals developed distinct chemical signatures that attracted additional shell builders while deterring predators adapted to different environmental conditions. Migration behaviors emerged as another strategy for dealing with temporally variable predatory pressure. Animals that could track and exploit seasonal changes in predator distribution gained access to resources and breeding opportunities that were unavailable to less mobile species. These migration behaviors required sophisticated navigation capabilities and energy storage systems that could support long-distance movement. The fossil record preserves evidence of early migration routes in sequential fossil deposits that track the movement of armored animal populations across ancient seafloor landscapes. Analysis of these deposits reveals migration timing, route selection strategies, and stopover site characteristics that demonstrate remarkable behavioral sophistication in early marine animals. Communication systems evolved rapidly during this period as the benefits of information sharing about predatory threats became increasingly important for survival. Early warning systems allowed armored animals to coordinate defensive responses across entire communities, multiplying the effectiveness of individual defensive capabilities. These communication networks required reliable signal transmission, message interpretation, and response coordination capabilities. The biochemistry of early communication systems reveals sophisticated molecular mechanisms for signal production, transmission, and reception. Chemical signals could carry complex information about threat type, location, and intensity, while remaining undetectable to potential predators. The development of species-specific communication channels allowed for secure information transfer within vulnerable populations. Predator detection systems became increasingly sophisticated as shell builders developed enhanced sensory capabilities for identifying and responding to threats. Early compound eyes provided visual threat detection capabilities that exceeded anything available to soft-bodied animals. The integration of visual, chemical, and mechanical sensing systems created comprehensive threat assessment networks. The neural processing capabilities required to coordinate multiple sensory inputs and generate appropriate defensive responses drove the evolution of more complex nervous systems during this period. Animals needed to rapidly assess threat levels, select optimal defensive strategies, and coordinate behavioral responses while maintaining essential life functions like feeding and respiration. Escape response systems evolved to take advantage of the enhanced protection provided by shells and armor. Animals that could rapidly withdraw into protective shells gained crucial seconds of safety that could mean the difference between survival and death. The biomechanics of rapid shell closure required specialized muscle systems and sophisticated coordination mechanisms. The engineering challenges involved in rapid shell closure included overcoming water resistance, coordinating multiple muscle groups, and maintaining seal integrity under pressure. The solutions preserved in Cambrian fossils reveal biological mechanisms that achieved closure speeds and seal effectiveness that rival modern engineered systems. Camouflage strategies also evolved in conjunction with armor development, as animals discovered that combining visual concealment with physical protection provided superior defensive capabilities. Early shell builders developed surface textures and color patterns that helped them blend with seafloor environments while maintaining structural integrity. The integration of camouflage with armor required sophisticated control over shell surface properties during construction. Animals had to coordinate pigment deposition, texture formation, and structural development to achieve optimal combinations of protection and concealment. These integrated defensive systems represent remarkable examples of biological multitasking. As we examine the full scope of innovations that emerged during this period of rapid armor evolution, we see the establishment of defensive principles that would continue to influence animal design for hundreds of millions of years. The fundamental engineering solutions developed by early shell builders, the integration strategies they discovered, and the optimization principles they established created templates for biological protection that persist in modern ecosystems. The speed and sophistication of these early innovations demonstrate the enormous creative potential that emerges when life faces existential challenges. Under extreme selective pressure, biological systems generated and tested new solutions at rates that exceeded anything seen in more stable environments. The armor revolution wasn't just about individual survival strategies. It was about the emergence of entirely new ways of living that fundamentally altered the trajectory of life on Earth. The legacy of this ancient arms race extends far beyond the specific innovations that emerged during the Cambrian period. Every time we observe rapid evolutionary responses to new threats or opportunities in modern ecosystems, we're witnessing echoes of the same fundamental processes that created the first biological armor over 500 million years ago. The creative explosion of defensive innovation that characterized the early Cambrian establish patterns of biological problem solving that continue to drive evolutionary change in contemporary marine environments. But as remarkable as these early armor innovations were, they represented just the beginning of an ongoing conversation between life and the physical world. The shells and spines that marked the start of the armor revolution would continue to evolve, becoming ever more sophisticated as predators developed new attack strategies and environmental conditions continued to change. The biological arms race that began with simple calcium carbonate tubes would eventually produce some of the most elegant and effective defensive systems in the natural world, each one building upon the fundamental innovations pioneered by those first brave shell builders in ancient Cambrian seas. The microscopic details preserved in these ancient shells reveal engineering solutions that would impress modern materials scientists. When researchers examine Cambrian armor under powerful electron microscopes, they discover construction techniques that rival contemporary composite materials in their sophistication and effectiveness. These weren't crude evolutionary experiments hastily assembled under pressure. They were precision-engineered biological systems that solved fundamental problems of protection, mobility, and resource management with remarkable elegance. The internal architecture of early mollusk shells demonstrates particularly sophisticated approaches to structural optimization. Rather than simply depositing calcium carbonate in uniform layers, these animals developed complex laminated structures where organic and mineral components were arranged in specific patterns that maximize strength while minimizing weight. The organic layers functioned like biological reinforcement fibers, providing flexibility and preventing catastrophic crack propagation through the shell. The mineral layers contributed rigidity and compression resistance. Most remarkably, the interfaces between these layers were engineered at the molecular level to ensure optimal stress transfer and prevent structural failure under extreme loads. But the real breakthrough lay in the biological control systems that coordinated shell construction. Building an effective protective shell requires precise regulation of crystal nucleation, careful management of organic matrix deposition, and exact timing of mineralization events across the entire growth surface. The cellular machinery necessary to coordinate these processes represents some of the most sophisticated biochemical engineering preserved in the early fossil record. Growth pattern analysis reveals that these early shell builders possess remarkable real-time construction management capabilities. Daily growth increments preserved in ancient shells show that animals could adjust shell thickness, modify internal structure, and alter chemical composition in direct response to changing environmental conditions or detected threat levels. This adaptive construction required sensory systems capable of monitoring external conditions and cellular mechanisms that could translate environmental information into specific architectural modifications within hours or days. The metabolic economics of early shell construction tell an equally compelling story about the evolutionary pressures driving armor development. Isotopic analysis of Cambrian shells reveals that animals building the most effective protective systems were investing enormous amounts of energy in their defensive infrastructure. Some species dedicated more than 60% of their total metabolic budget to shell construction and maintenance, representing one of the highest energy investments in protection documented anywhere in the animal kingdom. This level of metabolic commitment was clearly justified by the survival advantages provided by effective armor, but it also created intense selective pressure for efficiency improvements in every aspect of shell building biology. Animals had to develop enhanced feeding strategies to support their defensive systems, improved energy storage mechanisms to buffer construction costs, and optimized construction techniques that delivered maximum protection for minimum energetic investment. The relationship between shell chemistry and environmental conditions reveals another layer of sophistication in early armor systems. Animals living in different marine environments developed shells with distinct chemical signatures that were precisely tuned to local conditions. Species inhabiting deeper, colder waters incorporated different trace elements and isotopic ratios than those living in shallow, warm seas. These chemical adjustments optimize shell properties for specific environmental challenges while maintaining essential protective functions across diverse habitats. Geographical analysis of shell compositions across ancient ocean basins provides direct evidence for the environmental factors that influenced early armor evolution. Shells from equatorial regions show chemical signatures consistent with rapid growth in warm, nutrient-rich waters where predatory pressure was intense, but construction materials were abundant. Specimens from polar regions reveal slower growth rates, but enhanced structural density that provided superior protection against the larger predators that dominated colder marine environments. Seasonal variations preserved in shell chemistry demonstrate that early armored animals possessed sophisticated biological control systems that could adjust construction strategies throughout the year. Shells deposited during winter months often show increased density and altered trace element compositions compared to summer growth increments. This seasonal fine-tuning required integrated environmental sensing, metabolic regulation, and construction planning capabilities that approach the sophistication of modern biological systems. The damage repair mechanisms developed by early shell builders represent perhaps their most remarkable innovation. The ability to heal from predatory attacks provided enormous survival advantages, but implementing effective repair systems required solving complex biochemical and engineering challenges. Repair processes had to rapidly seal breaches in protective structures while maintaining structural integrity and eventually restoring optimal defensive properties. Evidence from repaired bore holes in Cambrian fossils reveals repair systems that could restore shell integrity within days of attack, fast enough to provide protection against the repeated assaults that many specimens clearly survived. The microstructure of repair zones shows construction techniques that differed significantly from normal growth patterns, indicating that animals could shift between normal construction mode and emergency repair mode, depending on damage assessment signals. Trace element analysis of repair tissues provides insights into the metabolic costs of shell healing. Animals diverted significant resources to damage repair, often depleting mineral reserves that would normally support other physiological functions. The speed and effectiveness of repair responses directly correlated with survival probability, creating intense selective pressure for efficient healing systems that could restore protection without compromising other essential biological functions. The integration of repair capabilities with normal growth processes required sophisticated developmental control mechanisms that could coordinate multiple construction priorities simultaneously. Animals had to balance investment in preventive shell thickening against reactive repair capabilities while maintaining optimal shell geometry for their specific ecological requirements. The solutions preserved in Cambrian fossils reveal biological engineering principles that successfully optimized protection across multiple timescales and threat scenarios. Competition between different shell-building lineages during this period drove extensive exploration of alternative construction materials and architectural strategies. While calcium carbonate eventually became the dominant choice for biological armor, early experiments included shells made from silica, phosphate minerals, and various organic composite materials. Each approach offered distinct advantages and limitations in terms of material availability, structural properties, and metabolic construction costs. Silica-based shells provided superior hardness and resistance to chemical dissolution, making them highly effective against predators that relied on shell boring or acid dissolution techniques. However, silica shells required different biochemical pathways for construction and imposed higher energy costs for repair processes. The limited availability of dissolved silica in many marine environments also constrained the geographical distribution of silica shell builders. Phosphate-based shells offered excellent strength-to-weight ratios and were particularly effective against crushing attacks. But phosphate availability was often limited in marine environments where this element was rapidly incorporated into other biological processes. Animals building phosphate shells had to compete with other organisms for access to this essential resource, creating additional ecological pressures beyond simple predator-prey interactions. Organic composite shells provided maximum flexibility and repair capability, allowing animals to absorb impacts that would shatter rigid mineral shells. These structures could also be constructed entirely from biological materials without requiring mineral extraction from seawater. However, organic shells offered less protection against predators with sharp cutting appendages and were more vulnerable to biological degradation processes. The eventual dominance of calcium carbonate shells reflects the optimal balance of material properties, environmental availability, and metabolic efficiency under early marine conditions. Calcium and carbonate ions were relatively abundant in Cambrian seawater. The biochemical pathways for calcium carbonate precipitation were metabolically feasible, and the resulting shells provided effective protection against the full range of predatory attack strategies that had evolved by this period. The experimental phase preserved in early Cambrian deposits reveals the remarkable range of biological solutions that emerged when life faced the fundamental challenge of protection for the first time. This period of rapid innovation established many of the basic architectural principles that continue to influence biological design in modern marine environments. The relationship between shell construction and reproductive strategies created additional evolutionary pressures that shaped armor development throughout this period. Animals with effective defensive systems could afford to invest more energy in reproduction, leading to larger offspring sizes, extended parental care behaviors, and more sophisticated mating strategies. The protective capabilities of shells also enabled entirely new reproductive approaches that would have been impossible for soft-bodied animals. Brooding behaviors evolved rapidly among early shell builders as parents gained the ability to protect developing offspring within their own armor systems. Modified shell chambers provided safe developmental environments while maintaining adult mobility and feeding capabilities. The engineering required to create structures that functioned simultaneously as personal armor and nursery facilities represents remarkable biological problem-solving under multiple design constraints. The timing and coordination of reproductive activities became increasingly sophisticated as shell builders developed enhanced abilities to predict and respond to seasonal patterns in predatory pressure. Many species evolved synchronized breeding events that temporarily overwhelmed local predator populations with more potential prey than could be effectively attacked. These coordinated reproductive strategies required communication systems capable of synchronizing behavior across entire populations. Chemical signaling systems evolved to support reproductive coordination behaviors across wide geographical areas. Pheromone production and detection capabilities allowed shell builders to communicate reproductive readiness and coordinate spawning timing, even when individuals were separated by considerable distances. The biochemistry of these signaling systems required molecular recognition mechanisms that could distinguish between species, specific reproductive signals, and general environmental chemical cues. Specialized reproductive armor represents one of the most elegant solutions to the competing demands of protection and reproduction that emerged during this period. Some early shell builders evolved modified defensive structures that provided enhanced protection during vulnerable reproductive periods while maintaining normal defensive capabilities throughout the rest of the year. These seasonal armor modifications required sophisticated developmental control systems that could coordinate structural changes with reproductive cycle timing. Extended parental care behaviors evolved rapidly as investment in individual offspring became more valuable when survival rates increased through effective protection. Early evidence for parental care includes fossilized shells with specialized brood chambers and protective structures specifically designed to shelter developing young. The metabolic costs of extended parental care required major adjustments in energy allocation strategies and reproductive scheduling. The integration of defensive and reproductive functions within single-shell architectures maximized the efficiency of expensive biological construction projects. Shells that could provide personal protection during normal activities while transforming into brood chambers during reproductive periods represented optimal solutions to resource allocation challenges. These dual-purpose designs required developmental control systems capable of coordinating multiple functions within single anatomical frameworks. Social behaviors also underwent rapid evolution in response to the new defensive capabilities provided by early armor systems. Group formation behaviors allowed individual animals with limited defensive capabilities to achieve collective protection that exceeded what any single individual could provide alone. The fossil record preserves compelling evidence of coordinated group behaviors that emerged directly from predatory pressure during this period. Mass mortality events from early Cambrian deposits show spatial arrangements of armored animals that strongly suggest defensive formations and cooperative protective behaviors. Groups of shell builders apparently coordinated their positioning to provide mutual protection while maintaining access to essential feeding opportunities. These behaviors required communication systems, leadership hierarchies, and individual decision-making capabilities that demonstrate sophisticated social cooperation emerging under extreme survival pressure. The chemical ecology of early shell-building communities reveals another dimension of social evolution during this transformative period. Animals that could coordinate chemical defense strategies achieved collective protection that proved more effective than individual chemical warfare approaches. Synchronized toxin production and coordinated chemical signal deployment created community-wide defensive networks that could deter predators across entire local ecosystems. Territory establishment and defense became increasingly important as shell builders developed the physical capabilities necessary to hold and protect valuable resources against competitors. The enormous energy costs associated with shell construction meant that access to high-quality food sources and optimal shell building materials became crucial factors determining survival and reproductive success. Competition for these essential resources drove the evolution of complex territorial behaviors and resource management strategies. Archaeological evidence from this period includes extensive fossilized shell accumulations that represent some of the earliest known animal construction projects. These shell middens, composed of discarded protective structures accumulated over multiple generations of shell builders, created elevated platforms and modified seafloor topography in ways that provided strategic advantages during territorial disputes. The construction and maintenance of these structures required coordinated group behaviors and long-term planning capabilities that demonstrate remarkable cognitive sophistication. Environmental engineering by early armored animals created positive feedback loops that enhanced the effectiveness of defensive strategies across entire communities. Shell accumulations and associated burrow networks modified local seafloor conditions in ways that favored the animals that created them while making environments less suitable for potential predators. These ecosystem engineering effects demonstrate how individual defensive innovations could create self-reinforcing advantages that persisted across multiple generations. Chemical modifications of seafloor environments by concentrated populations of shell builders affected local mineral availability, sediment stability, and water chemistry in ways that influenced entire marine ecosystems. Areas with high densities of shell-building animals developed distinct chemical signatures that attracted additional shell builders through positive feedback mechanisms, while simultaneously deterring predators that were specifically adapted to different environmental conditions. Migration behaviors emerged as another sophisticated strategy for dealing with temporally variable predatory pressure across different geographical regions. Animals that could successfully track and exploit seasonal changes in predator distribution patterns gained access to feeding opportunities and breeding sites that remained unavailable to less mobile species. These migration behaviors required sophisticated navigation capabilities and energy storage systems that could support extended long-distance movement. The fossil record preserves direct evidence of these early migration routes in the form of sequential fossil deposits that track the movement of armored animal populations across ancient seafloor landscapes over seasonal and annual timescales. Detailed analysis of these deposits reveals migration timing patterns, route selection strategies, and stopover site characteristics that demonstrate remarkable behavioral sophistication in early marine animals. Communication systems evolved with extraordinary rapidity during this period as the survival benefits of information sharing about predatory threats became increasingly critical for community survival. Early warning systems allowed armored animals to coordinate defensive responses across entire local populations, effectively multiplying the protective value of individual defensive capabilities through collective action. These communication networks required reliable signal transmission mechanisms, accurate message interpretation systems, and coordinated response capabilities. The biochemistry of early communication systems reveals sophisticated molecular mechanisms for signal production, transmission, and reception that approach the complexity of modern animal communication systems. Chemical signals could carry detailed information about threat type, location, intensity, and timing, while remaining undetectable to potential predators that might exploit communication channels for hunting purposes. The development of species-specific communication channels allowed for secure information transfer within vulnerable populations. Predator detection systems became increasingly sophisticated as shell builders developed enhanced sensory capabilities specifically designed for identifying and responding to various types of threats. Early compound eyes provided visual threat detection capabilities that far exceeded anything available to soft-bodied animals, while specialized chemical sensors could detect predator approach through waterborne chemical cues. The integration of visual, chemical, and mechanical sensing systems created comprehensive threat assessment networks. The neural processing capabilities required to coordinate multiple sensory inputs and generate appropriate defensive responses drove the evolution of significantly more complex nervous systems during this period. Animals needed to rapidly assess threat levels, select optimal defensive strategies from multiple available options, and coordinate behavioral responses while simultaneously maintaining essential life functions like feeding, respiration, and reproduction. Escape response systems evolved to take full advantage of the enhanced protection provided by shells and armor systems. Animals that could rapidly withdraw into protective shells gained crucial seconds of safety that often meant the difference between survival and death during predatory encounters. The biomechanics of rapid shell closure required specialized muscle systems and sophisticated neuromuscular coordination mechanisms. The engineering challenges involved in achieving rapid shell closure included overcoming significant water resistance, coordinating multiple independent muscle groups, and maintaining perfect seal integrity under external pressure from attacking predators. The biological solutions preserved in Cambrian fossils reveal mechanisms that achieved closure speeds and seal effectiveness that rival modern engineered protective systems. Camouflage strategies also evolved in close conjunction with armor development, as animals discovered that combining visual concealment with physical protection provided superior defensive capabilities compared to either strategy alone. Early shell builders developed sophisticated surface textures and color pattern systems that helped them blend seamlessly with complex seafloor environments while maintaining full structural integrity of their protective systems. The integration of camouflage capabilities with armor construction required precise control over shell surface properties during the entire growth and development process. Animals had to coordinate pigment deposition patterns, texture formation processes, and structural development programs to achieve optimal combinations of protection and concealment effectiveness. These integrated defensive systems represent remarkable examples of biological multitasking under severe design constraints. Advanced shell architectures that emerged during the later phases of this evolutionary period demonstrate increasingly sophisticated approaches to the fundamental trade-offs between protection and mobility. Animals developed shells with variable thickness patterns that concentrated protective material exactly where it was most needed, while minimizing weight in areas where lighter construction was sufficient. These optimization strategies require detailed understanding of stress distribution patterns and attack probability distributions. The development of articulated shell systems allowed animals to maintain high levels of protection while preserving essential mobility for feeding, reproduction, and escape behaviors. These jointed armor systems required precision engineering of hinge mechanisms, flexible connections, and coordinated muscle systems that could operate protective elements independently or in coordination depending on specific threat scenarios. Composite construction techniques became increasingly sophisticated as animals learned to combine different materials and structural approaches within single protective systems. Shells that incorporated both rigid protective plates and flexible connecting elements achieved optimal combinations of strength, weight, and mobility that exceeded what could be achieved through any single construction approach. The chemical warfare capabilities that evolved alongside physical armor systems added another dimension to defensive strategies during this period. Animals that could produce and deploy toxic or deterrent compounds through their shells created biochemical barriers that complemented physical protection mechanisms. The integration of chemical and physical defensive strategies required sophisticated coordination between multiple organ systems and represents early examples of combined defensive technologies. Toxin production systems had to balance effectiveness against metabolic costs while ensuring that defensive chemicals didn't interfere with normal physiological functions or shell construction processes. The biochemical pathways required for toxin synthesis, storage, and deployment represent major innovations in cellular biochemistry that emerged directly from predatory pressure. The success of early armor innovations created cascading effects throughout marine ecosystems that continue to drive evolutionary change long after the initial appearance of protective shells. Predators responded to improved prey defenses by developing specialized shell-breaking appendages, enhanced drilling capabilities, and sophisticated strategies for attacking vulnerable points in armored prey. This ongoing co-evolutionary process ensured continuous innovation pressure on both predators and prey. Shell-breaking specialists evolved powerful crushing appendages that could generate enormous forces concentrated on small areas of shell surface. The biomechanics of these attack systems required specialized muscle arrangements, reinforced skeletal elements, and sophisticated leverage mechanisms that maximized force application while minimizing energy expenditure. Drilling predators developed precision boring capabilities that could penetrate even thick shells through persistent mechanical abrasion. These specialized attack systems included hardened cutting elements, sophisticated positioning mechanisms, and chemical assistance that could weaken shell materials during drilling operations. Behavioral innovations by predators included coordinated group hunting strategies that could overwhelm individual armored prey through simultaneous attacks from multiple directions. These collaborative hunting behaviors required communication systems, role specialization, and tactical coordination that demonstrate remarkable cognitive sophistication in early predatory animals. The evolutionary response to these advancing predatory capabilities drove continued innovation in defensive technologies throughout the remainder of the Cambrian period and beyond. Animals developed increasingly sophisticated threat assessment capabilities, enhanced escape response systems, and improved armor designs that could withstand the latest predatory innovations. The fossil record from this period preserves direct evidence of this ongoing arms race in the form of increasingly elaborate defensive structures, more sophisticated repair capabilities, and enhanced behavioral complexity. Each new predatory innovation triggered corresponding defensive responses that maintain the delicate balance between predator effectiveness and prey survival. As we trace these developments through the fossil record, we see the establishment of evolutionary patterns that would continue to shape marine ecosystems for hundreds of millions of years. The fundamental principles of biological armor design, the integration strategies for combining multiple defensive approaches, and the optimization techniques for balancing protection against other essential functions all represent solutions that continue to influence animal architecture in modern environments. The speed and sophistication of innovations that emerged during this remarkable period demonstrate the enormous creative potential that biological systems can achieve when faced with existential challenges. Under extreme selective pressure, early marine animals generated and tested new protective solutions at rates that exceeded anything documented in more stable evolutionary environments. This ancient arms race established templates for biological innovation that extend far beyond simple predator-prey interactions. The problem-solving approaches, integration strategies, and optimization principles developed during the Cambrian armor revolution continue to influence how life responds to new challenges and opportunities in contemporary ecosystems. The engineering principles pioneered by these early shell builders laid foundations for biological design that persist across vast spans of evolutionary time. From the composite construction techniques that strengthen modern mollusk shells, to the integrated sensory systems that coordinate defensive responses in contemporary marine animals, the innovations of the Cambrian period continue to echo through the natural world. Perhaps most remarkably, this entire transformation from vulnerable soft-bodied communities to sophisticated armored ecosystems occurred within a geological instant. The compressed timeframe of the Cambrian armor revolution demonstrates that biological systems possess extraordinary capacity for rapid innovation when environmental pressures create urgent survival challenges. The legacy of this ancient period of biological creativity extends into every corner of modern marine life. Every shell, every spine, every sophisticated defensive behavior we observe in contemporary oceans can trace its evolutionary roots back to those first experimental armor systems that emerged in Cambrian seas over 500 million years ago. 100 million years ago. The sophistication of these early defensive innovations becomes even more apparent when we examine how they influenced the very fabric of marine ecosystems. The transition from soft-bodied to armored marine communities didn't just change individual species. It fundamentally altered how energy flowed through ancient food webs, how nutrients cycled through marine environments, and how entire ocean basins functioned as biological systems. Before the armor revolution, marine ecosystems operated on relatively simple principles. Soft-bodied animals filtered nutrients from water, grazed on microbial mats, or consumed organic debris that drifted down from surface waters. Predation existed, but it was largely opportunistic, based on chance encounters and simple overwhelming force rather than sophisticated hunting strategies. The introduction of vision-guided predators, armed with specialized attack capabilities, changed everything. Suddenly, every aspect of marine life became tactical. Animals could no longer simply exist in the water column or on the seafloor. They had to choose positions that balanced feeding opportunities against exposure to visual predators. They had to time their activities to avoid peak hunting periods. They had to develop escape routes and defensive protocols that could be activated within seconds of threat detection. This militarization of marine ecosystems created entirely new ecological roles that hadn't existed in pre-armored environments. Specialist shellbreakers emerged as apex predators, developing crushing forces that could crack open the most sophisticated defensive systems. Counter-specialists evolved enhanced armor thickness and chemical defenses specifically designed to resist these crushing attacks. The result was an escalating cycle of innovation that pushed both predators and prey toward increasingly extreme adaptations. The energetic costs of this biological arms race fundamentally altered how marine ecosystems allocated resources. In soft-bodied communities, most energy went directly into growth, reproduction, and basic maintenance. Armored ecosystems had to dedicate enormous resources to defensive infrastructure, attack capabilities, and the sensory systems needed to coordinate complex predator-prey interactions. This shift in energy allocation created new constraints on population sizes and community structure. Armored animals required higher quality food sources to support their expensive defensive systems. Predators needed access to sufficient prey populations to justify the metabolic costs of their sophisticated attack mechanisms. The result was more tightly coupled food webs, where changes in one component could cascade rapidly through the entire system. The chemical signatures of early armored ecosystems reveal the massive scale of biomineralization that occurred during this period. Entire seafloor regions became dominated by calcium carbonate production, as millions of shell-building animals extracted dissolved minerals from seawater and incorporated them into protective structures. This biological mining operation altered ocean chemistry on a global scale, affecting pH levels, mineral availability, and chemical gradients that influence marine life across vast distances. The accumulation of discarded shells created new types of marine habitats that hadn't existed in earlier periods. Shell beds provided hard substrate for attachment by organisms that couldn't survive on soft sediments. The complex three-dimensional structure of shell accumulations created microhabitats with different flow patterns, chemical conditions, and predation pressures than surrounding areas. These shellbed communities became centers of biological innovation as organisms adapted to exploit the unique opportunities provided by calcium carbonate substrates. Boring organisms developed capabilities to excavate homes within abandoned shells. Encrusting species evolved attachment mechanisms that could colonize smooth shell surfaces. Filter feeders positioned themselves to take advantage of enhanced water flow through complex shell structures. The geographical distribution of early armor innovations reveals how defensive technologies spread through ancient marine environments. Successful shell designs could propagate across entire ocean basins within a few million years, either through direct migration of armored species or through independent evolution of similar solutions in response to similar selective pressures. Ocean currents played crucial roles in this technological transfer, carrying larvae of armored species to new regions where their defensive innovations could be tested against different predator assemblages and environmental conditions. The most successful designs proved effective across diverse marine environments, while others remained specialized for specific local conditions. Climate fluctuations during the early Cambrian period added layers of complexity to armor evolution that extended far beyond simple predator-prey interactions. Sea level changes exposed and submerged coastal areas, creating new habitats while destroying others. Temperature variations affected metabolic rates, growth patterns, and the availability of dissolved minerals needed for shell construction. These environmental changes created windows of opportunity for evolutionary innovation as species encountered new challenges that existing defensive strategies couldn't address. Animals with flexible armor systems that could adjust to changing conditions gained advantages over those with rigid defensive approaches that worked well only under specific circumstances. The relationship between armor evolution and oxygen levels in ancient oceans proves more nuanced than early researchers anticipated. While higher oxygen concentrations provided metabolic fuel for expensive shell construction, many early armored animals actually thrived in environments with variable or reduced oxygen availability. This apparent contradiction reveals sophisticated physiological adaptations that allowed armored species to function effectively across diverse environmental conditions. Trilobites, in particular, developed respiratory systems that were specifically optimized for oxygen extraction in challenging conditions. Their gill structures included elongated filaments and expanded surface areas that could maintain adequate oxygen uptake, even when environmental levels dropped significantly. This adaptation to variable oxygen conditions may have provided competitive advantages in environments where less adaptable species couldn't survive. The integration of respiratory efficiency with defensive armor created design challenges that required innovative biological solutions. Animals had to maintain adequate gas exchange while protecting vulnerable gill structures from predatory attack. The solutions preserved in Cambrian fossils reveal sophisticated compromises between protection and respiratory function that optimize survival under multiple constraints. Seasonal patterns in early marine ecosystems became increasingly complex as armored animals developed enhanced abilities to track and respond to temporal variations in environmental conditions. Breeding cycles, migration patterns, and resource availability all influence the timing and intensity of predator-prey interactions in ways that hadn't occurred in simpler soft-bodied communities. Many early armored species evolved synchronized life cycles that concentrated vulnerable activities during periods when predation pressure was reduced. These temporal strategies required sophisticated environmental sensing capabilities and internal biological clocks that could coordinate behavior across entire populations. The fossil record preserves evidence of these seasonal patterns in the form of growth increments within shells that reveal annual cycles of rapid growth, alternating with periods of defensive thickening. These patterns suggest that early armored animals could predict and prepare for seasonal changes in threat levels through adjustments in shell construction priorities. Reproductive strategies underwent revolutionary changes during this period as animals gained access to protective capabilities that enabled entirely new approaches to mating and offspring care. The ability to survive direct predatory attacks meant that animals could afford to invest more energy in reproduction without compromising their own survival prospects. Extended mating rituals evolved as armored animals developed the protection necessary to engage in complex courtship behaviors that would have been suicidal for soft-bodied species. These elaborate displays often incorporated shell ornamentation and defensive posturing that served dual functions as both reproductive signals and threat displays. The development of specialized brooding structures within protective shells represents one of the most elegant solutions to the competing demands of personal protection and offspring care. These dual-purpose architectures required sophisticated developmental control systems that could modify shell geometry to accommodate developing young while maintaining defensive integrity. Chemical communication systems became increasingly sophisticated as armored animals developed enhanced capabilities for producing, transmitting, and detecting molecular signals. The ability to communicate threat information, reproductive status, and territorial boundaries through chemical channels provided enormous advantages in environments where visual communication might attract unwanted predatory attention. The biochemistry of these early communication systems required molecular recognition capabilities that could distinguish between species-specific signals and background chemical noise in complex marine environments. The development of specialized chemoreceptor organs allowed early armored animals to sample and analyze chemical information with precision that approached modern analytical capabilities. Territorial behaviors evolved rapidly as armored animals gained the physical capabilities necessary to defend valuable resources against competitors. The energetic costs of shell construction meant that access to high-quality feeding areas and optimal shell-building materials became critical factors determining survival and reproductive success. Archaeological evidence from early Cambrian sites includes territorial markers in the form of shell accumulations and modified seafloor structures that appear to represent early examples of animal construction projects. These engineered landscapes provided strategic advantages during territorial disputes while creating habitat modifications that persisted across multiple generations. The social implications of armor evolution extended far beyond individual protection capabilities. Group formation behaviors allowed animals with limited individual defensive capabilities to achieve collective protection that exceeded what any single organism could provide. These cooperative strategies required communication systems, leadership hierarchies, and individual decision-making capabilities that demonstrate sophisticated social coordination. Mass mortality events preserved in Cambrian deposits show spatial arrangements of armored animals that strongly suggest coordinated defensive formations. Groups of shell builders apparently position themselves to provide mutual protection while maintaining access to essential resources, behaviors that required complex social cooperation under extreme survival pressure. Environmental engineering by early armored animals created positive feedback loops that enhanced defensive effectiveness across entire communities. Shell accumulations and burrow networks modified local seafloor conditions in ways that favored the animals that created them, while making environments less suitable for potential predators. These ecosystem engineering effects demonstrate how individual defensive innovations could create self-reinforcing advantages that persisted across geological timescales. Areas with high concentrations of shell-building animals developed distinct environmental signatures that continued to attract similar species long after the original engineers had disappeared. Migration behaviors emerged as sophisticated strategies for dealing with temporal and spatial variations in predatory pressure across different marine regions. Animals that could successfully track seasonal changes in predator distribution gained access to feeding and breeding opportunities that remained unavailable to less mobile species. The fossil record preserves direct evidence of these migration routes in sequential fossil deposits that track population movements across ancient seafloor landscapes. Analysis of these deposits reveals migration timing, route selection strategies, and stopover site characteristics that demonstrate remarkable navigational sophistication in early marine animals. Predator detection systems became increasingly elaborate as shell builders developed multimodal sensory capabilities specifically designed for threat assessment. The integration of visual, chemical, and mechanical sensing systems created comprehensive early warning networks that could identify and categorize different types of threats with remarkable precision. The neural processing requirements for coordinating multiple sensory inputs and generating appropriate defensive responses drove rapid evolution of more complex nervous systems during this period. Animals needed to assess threat levels, select optimal defensive strategies, and coordinate behavioral responses while maintaining essential biological functions. Advanced shell architectures that emerged during the later phases of this evolutionary period demonstrate increasingly sophisticated approaches to optimizing protection while minimizing mobility constraints. Variable thickness patterns concentrated protective material where it was most needed while reducing weight in areas where lighter construction was sufficient. The development of articulated shell systems allowed animals to maintain high protection levels while preserving mobility for essential activities. These jointed armor systems required precision engineering of hinge mechanisms and coordinated muscle systems that could operate defensive elements independently or in coordination depending on threat scenarios. Composite construction techniques became remarkably sophisticated as animals learned to combine different materials and structural approaches within single protective systems. Shells that incorporated both rigid protective plates and flexible connecting elements achieved optimal combinations of strength, weight, and mobility that exceeded what could be achieved through any single construction method. The chemical warfare capabilities that evolved alongside physical armor added another dimension to defensive strategies during this transformative period. Animals that could produce and deploy toxic or deterrent compounds through their shells created biochemical barriers that complemented physical protection mechanisms. Toxin production systems had to balance effectiveness against metabolic costs while ensuring that defensive chemicals didn't interfere with normal physiological functions or shell construction processes. The biochemical pathways required for toxin synthesis, storage, and deployment represent major innovations in cellular chemistry that emerge directly from predatory pressure. Repair and maintenance systems became increasingly sophisticated as the value of expensive armor systems created strong selective pressure for effective healing capabilities. Animals that could rapidly restore structural integrity after damage gained enormous survival advantages over those with limited repair capabilities. The microstructure of repair zones in fossilized shells reveals construction techniques that differed significantly from normal growth patterns, indicating that animals could shift between normal construction mode and emergency repair mode depending on damage assessment signals. Metabolic integration systems evolved to coordinate the enormous energy demands of armor construction, maintenance, and operation with other essential biological functions. Animals had to develop enhanced feeding strategies, improved energy storage mechanisms, and optimized metabolic pathways that could support expensive defensive systems without compromising growth or reproduction. The success of early armor innovations created cascading evolutionary effects that continue to drive change throughout marine ecosystems long after the initial appearance of protective shells. Predators responded by developing specialized shell-breaking capabilities, enhanced drilling techniques, and sophisticated attack strategies that maintained pressure for continued defensive innovation. This ongoing co-evolutionary process ensured that neither predators nor prey could become complacent with existing capabilities. The result was sustained evolutionary pressure that continued to drive biological innovation throughout the Paleozoic era and beyond. The fossil record from this period preserves an extraordinary catalogue of biological experimentation, as life explored every possible solution to the fundamental challenges of survival in an increasingly dangerous world. Each fossilized shell, each preserved burrow, each trace of ancient behavior represents a successful answer to problems that had never existed before in Earth's history. The engineering principles developed during this period of intense innovation established design templates that continue to influence biological architecture in modern marine environments. The optimization strategies, integration techniques, and problem-solving approaches pioneered by early shell builders provided foundations for defensive innovations that persist across vast spans of evolutionary time. Perhaps most remarkably, this entire transformation from vulnerable soft-bodied communities to sophisticated armored ecosystems occurred within what amounts to a geological instant. The compressed time frame of biological innovation during the Cambrian period demonstrates the extraordinary creative potential that emerges when life faces existential challenges. The legacy of this ancient arms race extends into every aspect of contemporary marine life. Every defensive innovation we observe in modern oceans, from the composite shells of mollusks to the chemical defenses of sea slugs, can trace its evolutionary origins back to those first experimental armor systems that emerged over 500 million years ago. As we examine the full scope of changes that occurred during this transformative period, we see not just the emergence of biological armor, but the birth of modern ecological complexity. The simple act of building protective shells created cascading effects that fundamentally altered how life interacts with the physical world and with itself. The patterns of innovation, competition, and cooperation that emerged during the Cambrian armor revolution established evolutionary principles that continue to operate in contemporary ecosystems. Every time we observe rapid biological responses to new environmental challenges, we're witnessing echoes of the same fundamental processes that created the first armored animals in ancient seas. The story of early armor development reveals something profound about the nature of life itself. When faced with seemingly insurmountable challenges, biological systems possess remarkable capacity for creative problem-solving that can generate solutions of extraordinary elegance and effectiveness. The armor revolution wasn't just about protection. It was about the endless creativity of life finding ways to persist, adapt, and thrive in an ever-changing world. These ancient innovations continue to inspire and inform modern understanding of biological design, materials science, and evolutionary processes. The shells and spines that mark the beginning of biological warfare over 500 million years ago establish principles of biological engineering that remain relevant in contemporary research and technological development. The Cambrian armor revolution represents one of the most decisive turning points in the history of life on Earth. It marked the transition from a world of soft, vulnerable creatures to one dominated by sophisticated biological technologies that could resist, evade, and overcome the challenges of existence in an increasingly complex and dangerous environment. As we continue to study these ancient innovations, we gain deeper appreciation for the remarkable ingenuity of early life and the fundamental processes that continue to drive evolutionary change in the modern world. The first animals that dared to build protective shells didn't just ensure their own survival. They established patterns of biological creativity that continue to shape the evolution of life on our planet. The armor revolution that began over 500 million years ago is still continuing today, as contemporary organisms face new challenges and develop innovative solutions that build upon the fundamental principles established by those pioneering shell builders in ancient Cambrian seas. The creative explosion that transformed early marine ecosystems established a legacy of biological innovation that remains one of life's most powerful tools for ensuring survival in an unpredictable world. Redictable world. The fossil record reveals that this ancient arms race was far from over. As predators developed more sophisticated attack methods, prey species responded with defensive innovations that pushed biological engineering to its absolute limits. The evolutionary pressure was so intense that some lineages underwent complete morphological transformations within just a few million years, developing protective systems that would have been unrecognizable to their soft-bodied ancestors. Consider the remarkable case of early arthropods during the Middle Cambrian period. These animals faced a particularly acute challenge because their segmented body plans offered multiple potential attack points for predators. The solution they developed was nothing short of revolutionary. Rather than simply thickening their exoskeletons uniformly, they created articulated armor systems with specialized defensive zones that could function independently while maintaining overall structural integrity. The biomechanics of these early arthropod defense systems reveal engineering principles that wouldn't be formally described by human scientists for another 500 million years. Each body segment was equipped with overlapping protective plates that could slide over one another during movement, while maintaining complete coverage during defensive posturing. The joint mechanisms allowed for rapid transitions between mobile and defensive configurations, giving these animals tactical flexibility that proved crucial for survival. But the real breakthrough came with the development of active defensive capabilities. Some early arthropods evolved specialized appendages that could deploy defensive spines or chemical deterrents on command. These weren't passive protective features that simply absorbed attacks. They were dynamic defensive systems that could respond to specific threats with appropriate countermeasures. The neural control systems required to coordinate these active defenses represent some of the most sophisticated biological computing preserved in the early fossil record. Animals had to process sensory information about approaching threats, assess the optimal defensive response, and coordinate multiple defensive mechanisms within fractions of a second. The speed and precision of these defensive responses often determined whether an animal survived a predatory encounter. Meanwhile, early mollusks were taking an entirely different approach to the protection problem. Rather than developing complex articulated systems, they focused on perfecting the single-shell design through mathematical optimization of shape and structure. The spiral geometries that emerged during this period follow logarithmic growth patterns that automatically maintain optimal strength-to-weight ratios as the animal grows larger. The mathematics behind these shell designs reveals that early mollusks had somehow discovered fundamental principles of structural engineering through purely biological processes. The spiral forms they developed distribute stress loads evenly throughout the shell structure, while providing maximum internal volume for minimum material investment. These optimization principles represent biological solutions to engineering problems that human architects wouldn't formally solve until the development of advanced computational modeling. The internal architecture of early mollusk shells shows equally sophisticated engineering approaches. Rather than building solid protective barriers, many species developed chambered structures that provided buoyancy control while maintaining protective strength. These gas-filled chambers allowed animals to adjust their position in the water column for optimal feeding, while keeping their heavy shells from dragging them to the seafloor. The physiological control systems required to manage these buoyancy chambers represent remarkable innovations in biological engineering. Animals had to regulate gas pressure within sealed chambers, monitor and adjust buoyancy in response to changing conditions, and coordinate chamber construction with overall shell growth. The precision required for these operations approaches the sophistication of modern submarine ballast systems. Ocean chemistry continued to play crucial roles in determining which defensive strategies proved most effective during different periods of Cambrian evolution. Fluctuations in dissolved mineral concentrations affected the metabolic costs of shell construction, creating windows of opportunity for biomineralization, followed by periods when defensive investment became prohibitively expensive. Animals that could adjust their construction strategies in response to changing ocean chemistry gained significant advantages over those with rigid approaches to shell building. The most successful species developed flexible biomineralization systems that could switch between different construction materials depending on environmental availability while maintaining essential protective functions. The geographical distribution of different shell chemistries across ancient ocean basins reveals how environmental conditions influence defensive innovation on a global scale. Tropical regions with abundant dissolved calcium favored rapid shell construction and elaborate defensive ornamentation. Polar regions with limited mineral availability selected for efficient construction techniques that maximized protection for minimum material investment. These regional variations in defensive strategies created distinct biogeographical patterns that persisted throughout the Cambrian period. Animals migrating between different chemical environments had to adjust their shell construction techniques or risk metabolic exhaustion from inefficient biomineralization processes. The development of shell ornamentation represents another fascinating aspect of early armor evolution. While primary shell structure focused on protection and strength, surface ornamentation served multiple functions that extended far beyond simple defense. Elaborate surface textures could enhance camouflage effectiveness, provide additional grip surfaces for attachment, or create hydrodynamic features that improved swimming efficiency. Some of the most striking examples of early shell ornamentation include intricate rib patterns, spiral ridges, and complex node arrangements that required precise developmental control to produce consistently. The genetic and cellular mechanisms necessary to coordinate these ornamental features with essential protective functions represent major innovations in developmental biology. The fossil record preserves examples of shell ornamentation that clearly served social signaling functions in addition to protective roles. Size, symmetry, and complexity of ornamental features often correlate with shell size and apparent age, suggesting that these structures communicated information about individual fitness and competitive ability to potential mates and rivals. Chemical analysis of ornamental shell features reveals that some early animals invested rare trace elements in decorative structures, indicating that ornamentation represented significant metabolic expense beyond basic protective construction. This willingness to invest scarce resources in non-essential features suggests that social signaling provided survival advantages that justified the additional costs. The relationship between predatory pressure and ornamental complexity shows fascinating patterns throughout the Cambrian fossil record. Periods of intense predation correlate with reduced ornamental investment as animals focus resources on essential protective functions. Periods of reduced predatory pressure allowed for more elaborate ornamental development as animals could afford to invest in social signaling structures. Behavioral innovations continued to evolve alongside morphological changes as early armored animals developed increasingly sophisticated responses to predatory threats. Simple withdrawal reflexes gave way to complex behavioral repertoires that included threat assessment, graduated defensive responses, and coordinated group behaviors that multiplied individual protective capabilities. The fossil record preserves direct evidence of these behavioral innovations in the form of trace fossils that show coordinated movement patterns, defensive positioning, and escape behaviors. These preserved behaviors reveal tactical sophistication that rivals modern marine animals in complexity and effectiveness. Early warning systems based on chemical communication allowed armored animals to coordinate defensive responses across entire communities. Animals that detected approaching predators could release alarm signals that triggered defensive behaviors in neighboring individuals, creating community-wide protective networks that enhance survival for all participants. The biochemistry of these alarm signaling systems required sophisticated molecular recognition capabilities and rapid signal transmission mechanisms. Animals had to produce species-specific alarm compounds, detect and interpret signals from other individuals, and respond appropriately to different types of threat information. Cooperative defensive behaviors emerged as animals discovered that coordinated responses could repel predators that might successfully attack isolated individuals. Group formation, synchronized defensive posturing, and collective threat displays created protective capabilities that exceeded what any single animal could achieve alone. The social coordination required for effective group defense necessitated communication systems, leadership recognition, and individual behavioral flexibility that demonstrate sophisticated cognitive capabilities in early marine animals. These social innovations represent early examples of collective intelligence emerging under extreme survival pressure. Territorial behaviors became increasingly complex as armored animals developed enhanced abilities to defend valuable resources against competitors. The physical protection provided by shells and armor made it possible for animals to engage in prolonged territorial disputes that would have been fatal for soft-bodied species. Archaeological evidence from Cambrian sites includes territorial markers, boundary demarcations, and constructed defensive positions that represent some of the earliest examples of animal architecture. These engineered structures provided strategic advantages during territorial conflicts, while creating habitat modifications that persisted across multiple generations. The energetics of territorial defense required careful balance between the costs of maintaining defensive positions and the benefits of exclusive access to high-quality resources. Animals that could optimize this trade-off gained significant advantages over those with less efficient territorial strategies. Resource management behaviors evolved as animals learned to exploit territorial advantages for enhanced shell construction and reproductive success. Protected feeding areas provided access to high-quality nutrition that supported expensive defensive systems, creating positive feedback loops that reinforced territorial investment. Seasonal patterns in territorial activity reflect sophisticated understanding of temporal variations in resource availability and competitive pressure. Many early armored animals concentrated territorial investment during periods when resource defense provided maximum benefits, while reducing territorial costs during less favorable seasons. Migration strategies became increasingly sophisticated as animals developed enhanced capabilities to track and exploit seasonal changes in environmental conditions across different geographical regions. Long-distance movement between feeding and breeding areas allowed animals to optimize resource access while minimizing exposure to localized predatory threats. The navigational capabilities required for successful migration included landmark recognition, current sensing, and possibly magnetic field detection that enabled precise navigation across vast ocean distances. These sensory and cognitive abilities represent major innovations in biological information processing. Seasonal timing of migration events required internal biological clocks that could coordinate movement with optimal environmental conditions. Animals that could predict and respond to seasonal changes gained access to resources and breeding opportunities that remained unavailable to less temporally sophisticated species. Stopover site selection during long-distance migration required detailed knowledge of geographical resource distribution and predator activity patterns. The most successful migrants developed mental maps of suitable rest areas that provided adequate protection and nutrition during vulnerable travel periods. Environmental engineering by early armored animals reached unprecedented scales as concentrated populations began to modify entire seafloor regions through their construction and feeding activities. Shell accumulations created three-dimensional reef-like structures that provided habitat for numerous other species, while fundamentally altering local hydrodynamics and sediment transport. These early biogenic structures represent some of the first examples of ecosystem engineering by marine animals. The physical modifications created by shell builders persisted long after the death of individual organisms, creating legacy effects that influenced community development across geological timescales. Chemical modifications of seafloor environments by dense populations of shell builders affected local mineral cycling, pH levels, and nutrient availability in ways that created distinct biogeochemical signatures. These chemical changes attracted additional shell builders through positive feedback mechanisms while deterring species that were adapted to different chemical conditions. The spatial organization of early shell communities reveals sophisticated understanding of optimal positioning for resource access and predator avoidance. Individual animals position themselves to maximize feeding efficiency while maintaining protection through proximity to neighbors and defensive structures. Community structure patterns show evidence of species sorting based on defensive capabilities and resource requirements. Animals with similar protective needs and feeding strategies clustered together, creating specialized zones within larger community assemblages that optimized survival for all participants. Succession patterns in early shell communities demonstrate how initial colonizers modified environmental conditions in ways that facilitated colonization by subsequent species. These facilitation cascades created increasingly complex communities that supported much higher diversity than surrounding unmodified seafloor areas. The development of specialized ecological roles within armored communities created new opportunities for evolutionary diversification. Animals could specialize for particular functions within community settings, leading to adaptive radiation that produced numerous species from single ancestral forms. Symbiotic relationships began to emerge as different species discovered mutual benefits from close association within protective community structures. Early examples of symbiosis include cleaning relationships, shelter provisioning, and coordinated defense that provided advantages for all participating species. The biochemical innovations required for successful symbiotic relationships included recognition systems for identifying partner species, communication mechanisms for coordinating beneficial behaviors, and conflict resolution strategies for managing competing interests. Reproductive strategies underwent continued evolution as animals gained access to enhanced protection and resources through community participation. Group breeding events allowed for synchronized reproduction that overwhelmed predators while providing mutual protection during vulnerable reproductive periods. Extended parental care became increasingly elaborate as armored animals developed enhanced abilities to protect offspring through extended developmental periods. Specialized brooding structures, nest construction, and coordinated family group behaviors created unprecedented opportunities for offspring survival and learning. The integration of individual protective capabilities with community-level defensive strategies created multi-layered security systems that provided protection against diverse threats. Animals could rely on personal armor for immediate protection while benefiting from community early warning systems and group defensive responses. Advanced threat assessment capabilities evolved as animals learned to distinguish between different types of predators and adjust their defensive responses accordingly. Graduated response systems allowed animals to match defensive intensity to threat level, conserving energy while maintaining adequate protection. Chemical warfare capabilities became increasingly sophisticated as animals developed enhanced abilities to produce, deploy, and coordinate toxic defenses. Some communities developed coordinated chemical defense networks where individual animals contributed to collective chemical barriers that protected entire groups. The physiological systems required for effective chemical warfare included specialized glands for toxin production, delivery mechanisms for precise deployment, and detoxification systems that protected animals from their own defensive chemicals. These integrated chemical defense systems represent remarkable innovations in biochemical engineering. Predator specialization continued to drive defensive innovation as hunting strategies became increasingly sophisticated and targeted. Specialist shellcrackers, precision drillers, and chemical attackers, each selected for different defensive countermeasures, creating multiple parallel arms races within marine ecosystems. The co-evolutionary dynamics between specialized predators and their preferred prey created some of the most rapid evolutionary changes documented in the Cambrian fossil record. Lineages locked in intense co-evolutionary relationships underwent morphological transformations that occurred within hundreds of thousands rather than millions of years. Escape response systems reached remarkable levels of sophistication as animals developed enhanced abilities to detect threats and execute rapid evasive maneuvers. Coordination between sensory systems, nervous systems, and muscular responses achieved reaction times that approach the physical limits of biological systems. The biomechanics of rapid escape responses required specialized muscle arrangements, energy storage systems, and neural control mechanisms that could generate maximum acceleration within milliseconds of threat detection. These high-performance escape systems represent biological engineering achievements that rival modern athletic capabilities. Camouflage strategies became increasingly elaborate as animals learned to combine chemical, visual, and behavioral concealment techniques within integrated deception systems. Active camouflage capabilities allowed animals to adjust their appearance in real time to match changing environmental conditions. The neural and cellular mechanisms required for dynamic camouflage included sophisticated color change systems, texture modification capabilities, and behavioral coordination that could maintain concealment while performing essential life functions. Sensory system evolution accelerated as both predators and prey developed enhanced capabilities for detecting and interpreting environmental information. Multimodal sensory integration allowed animals to process visual, chemical, and mechanical information simultaneously for comprehensive situational awareness. The computational requirements for processing multiple sensory streams drove rapid evolution of more complex nervous systems during this period. Animals needed to integrate diverse information sources, assess threat levels, and coordinate appropriate responses while maintaining essential biological functions. Advanced shell architectures that emerged during the later phases of Cambrian evolution demonstrate increasingly sophisticated approaches to optimizing protection while maintaining functionality. Modular construction techniques allowed animals to customize their protective systems for specific environmental challenges and threat profiles. The engineering principles underlying these advanced shell designs include stress distribution optimization, weight minimization strategies, and multifunctional integration that achieved remarkable efficiency in biological protection systems. These design principles established templates that continue to influence biological architecture in modern marine environments. Material science innovations during this period included development of new biomineralization techniques, composite material construction, and surface treatment technologies that enhanced protective effectiveness while reducing metabolic costs. These biological material innovations represent major advances in natural engineering capabilities. Quality control systems evolved to ensure consistent production of high-performance protective structures. Cellular mechanisms for monitoring construction quality, detecting defects, and implementing repairs maintained structural integrity throughout the challenging construction process. The success of early armor innovations created evolutionary legacies that continue to influence marine life over 500 million years later. The fundamental principles of biological protection, the integration strategies for combining multiple defensive approaches, and the optimization techniques for balancing protection against other essential functions all represent solutions that persist across vast spans of evolutionary time. Modern marine animals continue to employ defensive strategies that can trace their evolutionary origins directly back to innovations pioneered during the Cambrian armor revolution. From the composite shells of contemporary mollusks to the articulated armor of modern crustaceans, the engineering principles established during this ancient period continue to provide effective solutions to the eternal challenge of staying alive in dangerous environments. The rapid pace of innovation documented during the Cambrian period demonstrates the remarkable creative potential that emerges when biological systems face existential challenges. Under extreme selective pressure, early marine animals generated and tested protective solutions at rates that exceeded anything documented in more stable evolutionary environments. This compressed time frame of biological innovation reveals fundamental principles about how life responds to crisis situations. The patterns of experimentation, optimization, and integration that characterize the Cambrian armor revolution continue to operate in contemporary ecosystems whenever organisms encounter new environmental challenges. The legacy of this ancient period extends far beyond simple protective technologies. The problem-solving approaches, cooperative strategies, and adaptive flexibility that emerged during the armor revolution established evolutionary patterns that continue to shape how life responds to change and uncertainty in the modern world. Perhaps most remarkably, the entire transformation from vulnerable soft-bodied communities to sophisticated armored ecosystems occurred within what amounts to a geological instant. This rapid biological transformation demonstrates that life possesses extraordinary capacity for creative adaptation when survival depends on finding new solutions to unprecedented challenges. The engineering achievements of early shell builders continue to inspire modern research in materials, science, biomimetics, and protective system design. The optimization principles they discovered through evolutionary processes provide insights that inform contemporary technological development and engineering innovation. As we examine the full scope of innovations that emerged during this transformative period, we see not just the development of biological armor, but the establishment of fundamental principles that continue to govern how life interacts with physical and biological challenges in the natural world. The armor revolution that began over 500 million years ago established a legacy of biological creativity and adaptive innovation that remains one of life's most powerful tools for ensuring survival in an unpredictable and often dangerous world. The creative explosion that transformed early marine ecosystems continues to echo through contemporary biological systems, driving ongoing innovation and adaptation in response to ever-changing environmental challenges. The story we've been tracing through these ancient seas reaches its crescendo, not with a single moment of triumph, but with the gradual realization that something fundamental had shifted in the very nature of existence itself. By the close of the Cambrian period, roughly 485 million years ago, the experimental phase of biological armor had crystallized into mature defensive systems that would set the template for marine warfare for hundreds of millions of years to come. What makes this transformation so remarkable isn't just the sophistication of individual innovations, but how quickly these scattered experiments coalesced into integrated biological technologies that solved multiple problems simultaneously. Animals that had started by simply secreting crude calcium carbonate barriers were now building precision-engineered composite structures that incorporated advanced materials science, sophisticated sensory networks, and dynamic response capabilities that could adapt to changing threat scenarios in real time. The fossil record from terminal Cambrian deposits reveals defensive systems that would look familiar to any modern marine biologist. Articulated shells with specialized joint mechanisms that allowed rapid deployment between mobile and defensive configurations. Chemical warfare capabilities that could deliver targeted toxins through integrated delivery systems. Collaborative defensive networks that coordinated community-wide responses to approaching threats. These weren't primitive approximations of modern systems. They were the genuine articles, fully functional biological technologies that had achieved remarkable sophistication through pure evolutionary innovation. But perhaps the most profound aspect of this ancient arms race was how it fundamentally altered the relationship between life and the physical environment. Before the armor revolution, organisms were largely at the mercy of environmental conditions, forced to accept whatever circumstances nature provided. The development of biological protection technologies gave animals unprecedented control over their immediate environment, allowing them to create protective microhabitats that could resist external pressures and maintain optimal conditions for survival and reproduction. This shift from passive adaptation to active environmental control represents one of the most significant transitions in the history of life on Earth. For the first time, organisms possessed technological capabilities that could modify physical conditions to suit biological requirements, rather than simply accepting environmental constraints as immutable facts of existence. The metabolic innovations required to support these expensive defensive systems created cascading effects that influenced every aspect of animal physiology. Enhanced feeding strategies, improved energy storage mechanisms, optimized circulatory systems, and sophisticated waste management protocols all evolved in direct response to the enormous energetic demands of biological armor construction and maintenance. So here we are, 500 million years later, still living in the world that those first shell builders created. Every time you see a crab scuttling across a tide pool, or watch a snail slowly navigating your garden, you're witnessing the direct descendants of that ancient biological revolution. The fundamental engineering principles pioneered in Cambrian seas continue to protect marine life today, proving that when life faces its greatest challenges, it responds with solutions of breathtaking elegance and effectiveness. The armor revolution didn't just change individual species, it transformed the very nature of existence itself, establishing patterns of innovation and adaptation that continue to echo through every ecosystem on Earth.